Alright, hell yes. We got material mechanics. This is chapter 1, but this is the last problem in the chapter. And it's double starred. You know what I mean? And so, how do you solve a double starred problem? So, this one's kind of worded weird. But in essence, is you have two bars that are the same. And I would just say they're solid. Their cross section for all purposes, might as well just make them square to begin with. That's going to make the problem easier. I would say that try to make all your dimensions 1. So even like right here, let's say that this thickness is like 1, and that might not make sense. I mean, yeah. If this is like 1 inch, let's say that's 1 inch. Now we know that maybe, hey, the cross-sectional area is 1 inch by 1 inch, and so that's 1 inch squared. The equations that we're using in this first chapter are sigma, or strength, is equal to force divided by area. And what we're looking at is the compressive stress or the length. So like, let's say you just had a bar hanging from the ceiling with a load on it. Well, then in the bar you're going to have the force is P and the area is that. So there you go, force over area, and strength is in PSI. So there you go. So we have we can figure out the PSI, and any material has a max PSI. So for steel, the strength is like 58,000 PSI, and this is pounds per square inch. So if I have a 1 inch by 1 inch steel rod, or bar, I can hang 58,000 pounds. I can hang I can hang basically a semi off of that. So just keep that in mind. The other aspect is that this length is L, and this is fixed. They're saying, hey, we have to have some sort of length out here, but now what we can do is we can make this bar any length. We can make it real tall, or we can make it like real short. But if we put it like right here, we still have to have that same P down. And what they're saying is we want to just use the least amount of material to get the job done and have the most amount of strength. And I don't read these, but I mean, you can read it while we do the problem. But essentially, said again, is that we want to use the minimal amount of weight. So maybe where does it say this? Determine this angle so the structure has minimum weight, and then it says without exceeding the allowable stresses. So now we just have to use, and then length, I'm going to say this is 1, even though that doesn't make sense. It's not 1 inch, but I don't know, maybe we should call it 10. So that's the first thing we'll do. We'll say, hey, we got 10 inches out here, and just visually it looks like this length is about 15. You know what I mean? So there you go. And at the end of the day, we need to figure out the weight, and it might seem difficult or trivial, I don't know what, but to find the weight of the bar, the equation for that, so let's say we just want, hey, the equation for weight is, well, we need to find the volume. So if we know the volume of the bar, then we know that, hey, there's a term called weight density, which is this, which is the force, like in pounds per volume, so like inches cubed. Cool. So if we know the volume, we can multiply it by the weight density, and that'll give us pounds. That'll give us pounds, because volume is going to be in inches cubed. Weight density is going to be pounds per inches cubed. You know what I mean? If this is steel, the weight density of steel is like 1/3 a pound. It's like 0.29 pounds per cubic inch. There you go. So even right here, we can kind of figure out the weight of this. Hey, if this is a 1 square inch by 1 square inch, we're going to have 10 of these square inches. and it's going to, each of these square inches is going to be 1/3 of a pound, so this thing's going to weigh maybe like 3 pounds. And then if this is 15, we're going to have 5 pounds. So right here we'd have 3 and 5 pounds. This configuration weighs 8 pounds. Cool. And I mean, we can all obviously make this configuration lighter, but now that brings up the other aspect of this. So let's say, let's see. So like I said, if we have 1 square inch, we can carry 58,000 psi. Does not mean we can put 58,000 psi here, but because we have angles, if we put 58,000 psi here, this member actually has to carry more. So if you go back to this one and say this is 58,000, well sure, this whole member inside this member is carrying 58,000 pounds. So this is in pounds, this is in pounds. But if we do the diagram here, is like, hey, this member can only take, so this member has a horizontal component and a vertical component. So even though it's like a physically drawn angle and its member is this long, you can treat this whole thing like a vector. You know what I mean? So this is the force vector that it can take, and I guess it would be in this direction. So this force vector has a component in the y and a component in the x. So if this component, this vertical component of this diagonal line or vector, this vertical component is the only thing that can take the 58,000. So just using geometry, if this is 58,000, and let's say this is 58,000, let's say it's a 45-degree angle, well then the force in this member is going to be 58,000 squared plus 58,000 squared square root of that. So let's just do that. So we got 58 squared plus 58 squared square root of that, and we get 82,000. You know what I mean? So we would have 82,000 pounds. So this is really good. This is what you want to do with complex problems. Any material mechanics problems, I always just say, hey, let's use steel. Most everything's made out of steel because you can weld it, you can have bars, and you can have 1 inch by 1 inch, gives you a lot of load, and the numbers aren't too big where things just start not making sense. Okay, but I already said, hey, if this is a 1 inch by 1 inch, I can only carry 58,000 because the strength of steel is 58,000 pounds per square inch. And right here, I have 82,000. So what we're gonna say is like, hey, this dimension on the bars is going to be 1 inch. But I'm going to say the thickness can vary. So now the cross-sectional thickness, it can vary. So the thickness might vary. So if I'm trying to carry this 82,000, I would have to make a thicker bar. By how much? Well, if it was double, 58 times 2. If this was 116,000 pounds, well, I would need 2 square inches, because 116,000 pounds divided by 2 inches squared, 2 square inches, that gets me back to that stress of 58,000 psi. And that is the pressure, you know, the force per unit area, that's the max pressure in steel. Okay, I don't have 116,000, I only have 82, so to find the thickness, I would say that 82,000 pounds divided by the area I'm trying to find can only equal 58,000 psi. So that just gets straight back to strength is equal to force divided by area. I want to find the area, and the area is going to be the width divided by the thickness. I know the width is going to be 1, so that's just 1 times the thickness. So at the end of the day, let's rearrange this equation for area, and area is equal to force divided by strength. Alright, more time on the clock and back at it. So we rearranged our strength equation for area. And then we did one more. We said that, hey, area is the width of the bar. Or I mean, like, we're saying this is width W. But then the depth is, or the thickness is T. So WT will give us the area, and that's F over sigma. And we're saying W is just 1 inch. So there you go. So basically at the end of the day, if this is 1, I mean, you can really say it's just 1 times T is equal to F over the strength. And this will give us T. T will be the force divided by the strength. And we just did that. It's 82,000 pounds that we're going to see in this member divided by the strength of steel, 58,000 pounds per inch squared. You see how the units cancel. Inches squared goes to the top. Obviously, we have 1 inch times T, so that one of these inches will cancel, and we'll be just left with T is equal to 82 divided by 58. The thickness will be 1.41 inches. Cool, in that member. Now we need to figure out, well, what's the reaction in this? Like, is this going to be in compression? We think so. If we're pulling down on this one's going to be in compression, and so we pulled down on this. This member is the only thing that can take a vertical. This component can't take any vertical force. So this vertical component of this member is the only thing that can withstand that 58,000 pounds, sorry, this should be pounds, that we're using as P. Once we do that, we establish that this horizontal, or the component in here, is a total of 82,000. Now we want to find this horizontal component, because this component has to be arrowed this way, and so now we're actually pulling, this component is pulling that way, this horizontal component right there. So we can just use what we know about angles, or tangents, sines and cosines. So how do you want to do it? I mean, well, we're saying that our angle is 45 anyway, so this is 58,000. So there you go. The force this way is 58,000. So this is pulling a force this way, and then so this member is going to have to balance that, and so it's going to see a compression force of 58,000. We're not going to do the free body diagrams, it's just kind of visual, and so we're going to say that this member right here has 58,000, therefore the thickness right here is just 1 inch. So there you go. So that we figured out that if we put a 58,000 pounds, we'll have to make this member thicker, and this member can stay the same at 1 square inch, just to make it work. But we go back to the problem. It says, hey, no, we have to use the same material in both of these. You know, we can't make this one thicker. This has to be a 1 inch bar, and this has to be a 1 inch bar. So in this configuration, we can't carry this 58,000. So now the question is, what load can we take? And if we go back to this diagram, this vertical component is the only thing that can withstand P. So we have to have an equation for however we got this 82,000. Then we have to use. All right, so let's do it. And if this is we're not going to use this angle right here. We're going to use this angle. So let's say this angle is 60 degrees. Because if it's 60 degrees, it's going to be more up like this, and we're going to be able to take more force. And so if this is the angle, sun is shining on the sine and component. So if this is the angle and you make a sun rays, this is what it's going to be shining on, and this is going to be the sine component. This part is going to be the cosine component. So this vertical component, you can either go a vector. You can either go this way and that way, or you can go this way and that way. So this vertical component, if this is 60, basically it says, hey, whatever this is, the force in AC is going to equal, or I apologize. So if you take this force, sine of the angle is going to be this component. So whatever, and this should make sense because sines and cosines are percents between 0 and 100%. You know what I mean? They're numbers between 0 and 1. So it's always going to be, and typically if you're not 90 or 0, it's going to be a number less than 1. So if we multiply our force by a number less than 1, we'll get this vertical component. Cool. So this is going to be, and this is essentially what the only thing that can hold P. So this is essentially what's going to hold P. But now what we want to find is what force, if we just choose a P, what force can we put in? So we just rearrange this equation for the force at AC, and that's going to be P divided by sine theta. So there you go. And let's try it out. If we do P divided by sine of 60 degrees. So the sine of 60 degrees, and you should know that you should know a sine of 30, 45, and 60 off the top of your head. This is 0.866. If we divide 1 by 0.86, and this is also just a ratio, 1 divided by 0.866 times P. So now we're taking 1 divided by a number smaller than 1, so this ratio is larger than 1. So it's a multiple of 1, and 1 divided by 0.866, so now we have 1.15 P. So what this says is that if we choose a P of 58,000, and we're not going to get this 82,000 anymore, yeah, I mean, if we choose a P of 58,000, so we're going to go 58,000 divided by sine of 60. Now the force in here would be 66,900 pounds. Okay, but what we want to do is be like, hey, we want to do the opposite and say this member can only take 58,000 pounds because that's the breaking strength of steel. It's a 1 by 1. So now we say that, hey, this force AC can only be 58,000. So we're going to rearrange this equation for P. For P. It's already rearranged for P. So we're going to say P is equal to 58,000, which can be the max force in this member, times sine of 60. And that's going to be 58,000 sine 60. Sine 60 is 0.866, so we get 86% of 58, and that gives us 50,200 pounds. So with a 60-degree angle, which is about like that, P can be 50,000 pounds. Cool. And if P is 50,000 pounds, what's the component here? Well, that's if this is our angle, sun is shining on the sine part, here's the cosine part. And if that's hard to see, here's the vector of AC, and then here's the vertical part, here's the horizontal part. So this is the part pushing this way. Now this can only take that horizontal component. So whatever this is equal to our reaction, our compressive force at BC. So what is this component? Well, here's our angle. Sun is shining on the sine, and this is the cosine part. So we say we take the hypotenuse, which is the force at AC, times cosine of the angle. So this is going to be your larger force, and now we're multiplying it by a percent, between 0 and 100%. That's what cosines and sines are. At the end of the day, cosines and sines are just fractions of the whole. It's like, hey, I have like a force of 500. What is this? Well, just by visualizing, if this is 500, this looks like 350. You know what I mean? 300, 400. All right, more time on the clock. All right, hell yeah, back at it. So now we have an equation that says the force of BC. I mean, well, this is going to give us the force of BC. So if we take the force of AC times the cosine, we get the force at BC. Cool. So now we have an equation for the compressive force in this member, and it's a function of force of AC. But now this is the first time that we kind of have to combine two equations, because right here we said the force of AC was sine theta. So let's write that. Force of AC sine theta is equal to P. And it's this P. Now we have an idea that it's the force that we want. We want to be able to put the max force here. I mean, that might be one way to put it. And making sure the weight of these members are light. Are in the lightest configuration. I mean, because, like we said, if this thing, and then we do have upper limits. Like if we take this member and make it almost vertical, so long that this angle is basically vertical, this member is going to be real heavy. But it can take its full max load, and for a 1 inch by 1 inch bar is going to be 58,000. I mean, so that right there is a good verbal understanding of this problem. Hey, if I'm working with 1 inch by 1 inch steel, it's only so strong. I can only put 58,000 pounds on it because breaking point of steel is 58,000 pounds per square inch. If the PSI in this member gets to 58,000 pounds per square inch, it's going to break. And so we make it really long. It's basically like hanging it from the ceiling. So if we have a 1 inch by thickness of 1 inch, square rod, I can only put 58,000. I can't put more than that. That's what I'm getting at. You know what I mean? I can't put more than that. So that configuration would be like, whoa, this rod is hanging like 20 feet up. The angle's real shallow. But now our system is just real heavy. Like that's a bad design. It's just too much material. It costs too much. And we can still only get the 58,000. So what we do is we be like, hey, let's do that 60-degree angle. And we tried that, and we're able to still capture 58,000. And we just reduced our weight from 10 feet to, just 2 feet. You know what I mean? So we just cut the cost by a fifth. You know what I mean? So now we just have a fifth the cost. So that's what this problem is getting at. It's like, well, now why don't we just get rid of that member? Well, we have a hinge here, and you won't be able to carry any weight. And then what if this member was all the way down to here? Well, and then just right there. Well, it's going to put only so if we put that member down here, only the vertical component of this member can carry this P. And that vertical component is just real tiny. You know what I mean? It's identical to having a slack line. And if your angles are real small, like a 200-pound person can generate a 10x, 2,000 pounds, like a 10x of force in this webbing. You know what I mean? So that's what happens when angles get small for certain things. Okay, so let's go back to this horizontal equation, because we said, hey, we know that this horizontal component is going to be whatever the force is in this member, cosine of it. So we have the force in this member, cosine of it is going to be this compressive force right there. And we know that this FAC is part of this equation. So now we can rearrange for FAC. FAC is P over sine theta. So let's take this equation and put it right into there and get a new equation where we got P over sine theta times cosine theta is the compressive stress in this member. Cool. And we can see that sine, you should know that tangent theta is sine of the angle over cosine of the angle. And so I see a cosine on top and a sine on the bottom. I see a cosine on the bottom, sine on top. So 1 divided by tangent is cosine on top, sine on bottom. And that's what I see. So I'm going to do P over tangent of the angle is equal to that force, that compressive force in BC. So that is our other equation. Cool. So now let's, I'm going to write these three equations, new sheet of paper, and then we'll start from there. Alright, heck yeah, we're back at it, and we kind of wrote these equations down. So we went real simple. We said, hey, at some point I'm going to know the force in this one, and it's going to have a horizontal component, and so that's going to be the force in BC. So I'm going to say whatever the force in AC is, force in AC times the cosine of this theta is going to be the force in BC. Cool. And then force of AC times the sine is going to be the vertical component. So if this is the vector this way, it's going to be the vertical component there. This is the horizontal component. And that's going to be the sine of this angle. Like obviously, this one right here is the same as this one over there. So that's going to be force of this AC times the sine of theta is going to be P. It's the only thing that can hold up this P. This vertical component here is the only thing that can hold up that force. Okay, cool. And you can rearrange for force of... and then so what we want to do is rearrange for force of AC and force of BC in terms of P. So that's what we did. So the force of this compressive member is P divided by tangent theta, and the force in AC, this one, is P divided by sine theta. Alright, but we should probably rearrange these, because at the end of the day, it was the P that we wanted to find. What's the max force if we have, whatever arrangement? So we're just gonna rearrange. Well, let's do this one first. P is equal to the force of AC times sine theta. Yeah, I don't know if that's where I want to go with this. But then this one is P is equal to the force of BC tangent theta. Alright, so now we have that relationship, but like right here is where I would be like, okay, I got to a spot where I'm just like, well, I don't know what to do. So what I do is like, hey, throw in a couple values. So we're going to throw in theta is equal to 60, and then we're going to throw in theta is equal to 30. Anytime you have angle problems, I stay away from 45, because sine of 45 and cosine of 45 are both the same, but they're not representing the same thing. If this is the sunshine and this is the sine component and this is the cosine component, just because sine of 45 is the same as this component, you know what I mean? Or the cosine of 45 is the same as the sine component. So that's why I use angles of 30 and 60. So all right, so let's do it. So if the angle is 6, let's go back to that one. If the angle is 60, the max P that I can have is well, yeah, and that's why picking a material and picking a breaking strength of steel is 58,000. So I know, and we have an area of 1 square inch because our width and thickness is 1 square inch on both of those. So I know that the force of AC, so the force of AC max is 58,000. And the force of BC is 58,000. But I know this is going to be probably the limiting factor right here. So force of AC, and so if I know that, the force of AC, then I can find, so if I know the force of AC, I can find P. So I'm going to use this equation. So we have a couple, this equation is related to P, and then P is a function of force of AC, and then this is P as a function of there you go. So now we're on the right path. I'm going to say, hey, if or let's do it. So force of AC is 58,000 pounds. We're going to use this equation. Sine of 60 is equal to what? Sine of 60 is 0.866. Cool. So we have that 86% of 58. So now even before we type this into our calculator, we kind of know what answer we're going to get. It's like 50,000. Okay, so 58,000 sine of 60 is 50,200 pounds. Cool. Once I know that, and it's I should kind of go all the way. There you go. And I'm going to store that as x. So that is the vertical component. Now the horizontal component, or the force in BC, is going to be this 58,000 cosine of the angle. So there you go. And then we'll go back to our equation. Does that make sense? P is equal to that 58,000. No, the force of BC. Where's our equation for that? Well, I guess I have it right here, but obviously I can say the force of BC is equal to the force of AC cosine theta. So this equation is the one that I was looking for. So these two equations will get us oh, well, it's actually just a check on reality. So if I say, hey, we already maxed this member out, so if I max this member out at 58,000 pounds, sure, the vertical component is going to be 50. The horizontal component is going to be that 58. Let's get some more light in. Okay, so this horizontal component is going to be this vertical component, which we maxed out, 58,000 pounds, cosine of 60. Cosine of 60 is 0.5. So cosine 60, that's 0.5. So it's 58,000 times 0.5, which is 29,000 pounds. And what information this gives us is like, hey, if this member gets maxed out, there's hardly any force on this. You know, this member has hardly any force on it at all. Okay, so cool. And we can even, since we have this relationship, the next angle, let's go up to 80 degrees. So now we have something like this. So this member is really long. It can still only carry 58,000. The vertical component is going to be very useful. So if this is our angle of 80, we know that we can only carry 58,000 in this member. The vertical component is going to be 58,000 sine. Here's our angle, sun shining on the sine end. 58,000 sine of the angle, and that makes sense because this is the max we can put in this. And we're taking a percentage. Only a percentage of it is in the vertical direction. And that's what sines and cosines are. They're percentages of the whole. Percentages between 0 and 100%. Sine of 80 is a pretty large number. It's probably like 92%. Sine of 80 is, oh, no, it's 98%. So there you go. Sine of 80 is 98.5, basically 98.5%. All right, so 58,000 sine of 80 gives us 57,119 pounds. That's going to be what we can, that would be P. It's the vertical component. So we could carry 57,119 pounds. Now we're going to see the reaction in BC, which is this 58,000. It doesn't change because the cross-sectional area is still just 1 square inch. The strength of steel can only take 58,000 psi, pounds per square inch. But now that we're more vertical, the horizontal, so it's basically taking this 158,000. The vertical component's very similar, but the horizontal component's probably real small. And that's going to be 58,000 cosine of 80. So 58,000 cosine of 80 is this horizontal component. Cosine of 80 is the same thing as saying sine of 10. And sine of 30 is 0.5. And then it's a linear relationship. So sine of 15 is 0.25. So sine of 10 must be like 0.19. So sine of 10, it's like 0.17. So at least we were pretty close. And what that means is only 17% of 58,000 is going to be seen in this compressive stress, in this horizontal component. 58,000 sine of, cosine 80. Cosine 80. Alright, heck yeah. And this is I think the only way that you're actually going to get an intuitive development, kind of going slow, setting up symmetry, doing a problem, and having the mental capacity to keep doing it again and again. Like, hey, we did 60 degrees. I have the mental capacity to change it to 80 and then figure out the numbers. It's just running two equations, but then really slowing it down and being like, hey, this member can only carry 58,000. It has a vertical component, which is basically all of it, 98%, and has a horizontal component. The horizontal component isn't just 2%. No, I mean, that's not how angles work. It's 17%. You know what I mean? You can say, hey, this length right here, this is 17 or 20, like basically 20. You could go 1, 2, 3, 4, 5. So this isn't an 80 degree, this is about a 70 degree angle. But anyway, so we got this 58,000 cosine of 80. And that's 10,072 pounds. So if we make our angle 80, the compressive stress in this is real low. You know what I mean? But we can only put, it wasn't valuable to do that. We used like 5 times more material, and sure, we were able to eke out a little bit more. We went from being able to carry 50,000 at P to 57,000. But we spent 5 times as much money, you know what I mean? Because it's 5 times heavier to buy all this steel. So now let's start going the other direction, and we'll go to 30. So we're going to go theta is equal to 30 degrees. So now we're like down here. So now this vertical component, what you should know about 30 degrees is that the vertical component, the sine component, is 50 or 50%. It's 0.5. So we're going to say, hey, this member, it's still 1 square inch, can only take 58,000 pounds because the strength of steel is 58,000 pounds per square inch. Half of that is going to be 25, 28, 25, 29. So half of 58 is going to be 29,000 pounds. And the equation for that is, hey, force of A sine of theta. Force of A is 58,000 pounds sine of 30 degrees. That's going to be 0.5, 50%. That's going to be this 29,000 pounds. So so then P can only carry 29,000. And then the compressive stress is going to be this 58,000 cosine of 30. Well, if this is 50%, this is 0.866. So knowing the sine and cosine of 30 degrees by heart is very good, because 0.86 is 86%. You know, and in general, this is almost 100%. You know what I mean? So if the compressive stress is 58,000 in this member, you know, it's basically 58,000 in this member. It's 85%. So let's do that. So the compressive stress, or the force in BC, is going to be 58,000 cosine of 30, which is 58,000 times 0.866. And that's going to be 58,000 cosine 30. That's going to be 50,229 pounds. Okay, so at 30 degrees, what we see is that our P is only 29, you know what I mean? So now we can't carry much load at all. We can carry about half the load at 60, and at 60 degrees, so 60 degrees is basically here, and 30 degrees is here. Let's say we use, and this is 1, 2, let's say, so material-wise, let's say this is 1 and 2, so we use 2, and then this is 1, 2, 3. So at 60 degrees, we're using like 2/3 more material. We're using we're having to buy $3 worth of materials compared to $2, or $300 worth of materials compared to $200. But if we buy $300 worth of materials, we get twice as much load. You know what I mean? So that is kind of a bang for the buck, Because if we spend $200, well, it's just a bad design and we only get half the load. So hey, let's spend more money, $300, and get twice as much load. That makes sense. And in this problem, material weight is the same thing as cost. If they're saying at what angle is the weight the lowest, and at face value, you're just like, who cares? Like, I don't really care. Like, you know, what am I trying to do? Like, reduce the weight? I mean, something that can carry 58,000 pounds, why am I concerned that it weighs 25 pounds instead of 20 pounds? Is because steel costs a lot, and your cost might be, you know, depending on if this is fancy metal and cost a lot, you know, your cost might be between 300 and 200. So right now, maybe there is a middle range between 30 and 60. And so let's grab a new sheet of paper and let's just say 45 degrees. And at this point, this would be a good time to do 45. Again, steel, 58,000 pounds per square inch. We're going to say the area is 1 square inch. That's where we get the max force in this member can be 58,000. So the vertical component is going to be, the vertical component is 58,000 sine 45. So P is equal to 58,000 sine 45. Sine 45 is 0.707. It's 70.7%. It's a really good one also to memorize. So 58,000 times sine of 45 is going to be 41,013 pounds. Cool. And if that's the vertical component, what's the horizontal component? Well, it's going to be this 58,000 cosine of 45. So, oh, and I should say that this is P, but this is going to be your force at BC. And that's going to be 58,000 cosine of 45. Same number, 41,013 pounds. So, is this the largest number that we've come up with? Well, no, it's not the largest. So this equation is not about the largest. It's about the bang for the buck. We said if this angle gets really steep and we got like 20 feet of this, our cost is going to be like 10 times. You know, we have $1,000 cost and we're only eking out 58,000. We move it to 60. Hey, we get a compress. If we go to 60 degrees. We're right at that 50,000. We're 60 degrees on here. I think it's 60 degrees is right there. Hey, we can generate 50,000 of P, but it's going to cost $300. If we go to 30 degrees, we're only going to generate half that, 29, and it's going to cost 200. So let's go to a 45 degree angle, and now it looks like, hey, we're still. There's almost no material difference between 45 and 30. Look at the material difference. This looks like 1, this looks like 1, maybe like 1.2. You know what I mean? So instead of our costs and 60 degrees, you know, it felt like 1, 2, 3. It felt like this one was going to cost $300. It felt like this one was going to cost $200. And this one was going to cost $120. I'm sorry, $220. This one we could generate 50 kilonewtons. This one we could only generate 29 kilonewtons. And this one we're generating 41 kilonewtons. This was the 45 degree angle. So even just right now, you know, can we get kind of a way to be like, well, I'm spending $200 and I'm getting half the strength of this, like half the strength I know the steel can take. Well, okay, that's a starting point. So let's spend $300 and get the most, but $300 is a lot of money, and so let's spend almost that same $200, just $20 extra, and I get pretty darn close. I get halfway between. So look at this. So for $20 extra, I get halfway between these two numbers. Or I can spend $100. More time on the clock. Okay, cool. Or I can spend $100 and get 50, you know what I mean, and get close to that max. Or, like I said, we can make the angle like 80 or 85 degrees, and this thing is going to be 20. It's going to be like basically 19 of these shapes, 1 through 19, and then this will be 20. So that's going to cost $2,000. So if we spend $2,000, we can literally make P 58 kilonewtons. But look at that. So this is your return. If we make the angle less than 30, holy Toledo, you know, we're still spending that same 200. Any angle less than 30, you're still spending 200. So let's do that one, because that kind of fleshes it out. Let's say we do a 5-degree angle. This was 58,000. That means the vertical component is going to be 58,000 sine of 5 degrees. And we can do this one on our head. Sine of 30 is 0.5. Sine of 15, that means that's 0.25. Let's keep halving. Sine of 7.5 is 0.125. And half of that, sine of 3.75 is 0.06. So it's like 6/8. So let's say 8%. Only 8% of 58. So 58,000 times 0.08. Only 4,640 pounds. But let's do it for real. 58,000 sine of 5, and we get 50,000 or 5,000 pounds. So if we spend the same $200 but do a really shallow angle, or, you know, maybe it's $195. You know what I mean? And we can get 5 kilonewtons. So right here, for $5 more, we can get 29 kilonewtons. So plus $5. That sounds like a really good deal. For $20 extra, we can get another 10 kilonewtons. Like this is 30 kilonewtons. Why don't we get an extra 10 for only 20 bucks? We're already spending $200 for 30 kilonewtons. We'll spend an extra $10 and get 40 kilonewtons. Or we can spend an extra $100 and get 50 kilonewtons. But that's an extra 100. And like I said, if we spend $2,000, we're only getting 58 kilonewtons. We're only getting 8 more kilonewtons. So this would be $1,700 extra dollars just to get another 8 kilonewtons. That is not worth it. So at some point you get the magic number. You know what I mean? And I don't know. At some point it might be subjective. Maybe for the purposes of what we want, you know, hey, I'm okay with spending $300. We're already in $200. $300 doesn't sound like a bad deal, and we basically get the most. We can basically take the material to pretty close to its limit. For this problem, kind of the answer in the back of the book is this 45-degree angle. They're saying, hey, this is going to be the best weight, because the question says, what's the lowest weight? So right here, hey, we have a weight of 3, and we're getting this. But hey, we can have a weight of 2.2, so this is fairly light, and we're still getting the best. This seems like the best bang for the weight. If we're really weight conscious, you know what I mean? If we really, that's a good way to put it, because dollar wise, it's like, well, yeah, this is excessive. 300 might be excessive, but you know, maybe there is a window between 200 and 300 that might be still a little bit of a Goldilocks number. But right here is where your return on your investment is max. And so now we have to find equations to show that. Because at the end of the day, if you're really good at math and calculus, you don't have to do this process of guessing and checking. But for these harder problems, I would throw something at it and see why that arrangement is what it is. And then see what they're asking. And then go, once you have a thorough understanding of like, okay, now I know the range they're talking about. Now we can develop some of those equations. So let's print off some more paper and catch you on the flip side. Alright, heck yeah. So we're back at it. And this is probably going to be one of the harder parts of solving this problem. is actually going back to be like, well, what is it asking us to do? It's like we have to reduce the weight, and we know that maybe the strength, is only so much. So we definitely want this equation. Strength is force over area. I would definitely write the equation for weight. Weight is going to equal, it's going to equal the volume. Sometimes I just like to write this out, times the mass density, which is like pounds per volume. Cool. And then so how do we find the volume? Well, volume is going to be the area times the length. You know what I mean? That makes sense. Area is in inches squared, length is in inches, then we get a volume in inches cubed. This weight density is pounds per inches cubed. So cool. Then those can cancel and we'll be left with pounds. Alright, so and we're saying, hey, at the beginning I said, hey, we can maybe increase the thickness, but no. For this one, we're just going to buy 1 inch by 1 inch. Area is equal to 1 inches squared. So this is going to be constant. So now, a lot of these complex problems is like anytime that you get something that's constant, you know what I mean? You can almost, well, in this case, if we can choose whatever we want, let's definitely make it 1. So weight is going to be 1 times length. And at the end of the day, basically, we're basically kind of saying weight, weight is length times the unit density. Cool. So we're basically saying weight is 1 times length times the unit density. And unit density of steel is 0.29 pounds per inch cubed. But again, also here, let's say we're using something heavier, I don't know, like tungsten. Like maybe whatever the heaviest, steel's got a density of 7. If we had something with a density of 21, and I think some of the heaviest metals get up to a pretty high density, close to a density of 20. At least 17, mercury's 16, 17, 18. Probably not 21, but let's just invent our own metal that has a weight density of 1 pound per inches cubed. Well, great. Then this becomes 1 too. So we can, at the end of the day, say our weight is going to be 1 times length times 1. And now we can basically say our weight is length. You know what I mean? So that's, for our problem, for all intensive purposes, weight is length. And the more professional way to do this, I think, weight is I think they use this term for proportional. Weight is proportional to length, or weight is equal to a constant times length. So even if we did use steel, at the end of the day, weight is going to be some sort of constant times length. But it might be, for our brains, it might be easier just to say, hey, wherever, if I want to use weight, I just use length. Or in reverse this, anytime that I see length, I'm just going to kind of basically say that's the weight. Cool. I'm going to kind of foreshadow right to what I did not understand until I kind of wrote all this stuff out to be like, oh, hey, even in this configuration, what do you think this is? Let's say this is a 3, 4, 5 triangle. A lot of different ways to get the angle. But the easiest way to get the angle, especially if you know both sides, is we're going to say tangent of the angle is opposite over adjacent. And you can know that because this is the sun shining, this is the sine part, and this is the cosine, the adjacent part. We know tangent from memory is sine theta over cosine theta. Tangent is opposite over adjacent. And so we can say tangent of the angle is 4 over 5 for this picture. And then we can rearrange this equation and say, hey, the angle is the inverse tangent of 4 over 5. So inverse tangent of 4 divided by 5, this angle is going to be 38.7 degrees. We're going to store that into our calculator as theta. And now let's figure out what the weight of these bars, in this configuration, what is the weight of the bars? Well, we're going to say the weight of the bars is the length. Cool, so let's just find the length of these bars. Now again, for our problem it says, hey, this length of L is fixed. So why don't we just call this 1. And now I get it. It doesn't make sense to call this 1 inch. But just pretend 1 inch is much larger. You know, we kind of want to call this 10 inches. So, you know what I mean? Should we just call it 10 inches for now and then go back and get rid of it? So yeah, this length for visual purposes, it's going to, for us right now, it's going to be 10 inches. If this is 10 inches, what's this length? Well, visually it's more. You know what I mean? If this is a 3, 4, 5 triangle, 10 is to 3 as, so we'd go 10 divided by 3 times 4. You would get this. This would be 13.3, and this would be 10 divided by 3 times 5. This would be 16.6. But now let's use our angles and what we know. If this is our angle, and this is our hypotenuse, we know, and we know that this is the sunshine, and this is the cosine in part. What do we know? We know that our hypotenuse times the cosine of the angle is L. So whatever way, and I know like if you're in middle school math, you don't learn it this way. In engineering, you always know, hey, I got a vector or a length that's diagonal, and I want to know the horizontal components or the vertical components. We do that all the time. So this is the equation that's just kind of the bread and butter. Like taking the hypotenuse, taking the vector, and finding the horizontal component just by... And this one makes the most sense because we're taking the longest. The horizontal component is the longest component, and then we're going to take a percentage of it to get the other components, the horizontal component and the vertical component. H sine theta is the other one. H sine theta would be... you know, this vertical component or whatever. Cool. Middle school students learn it as, hey, sine theta is equal to opposite over hypotenuse. Cool, you could have done that too. And cosine theta is equal to adjacent over hypotenuse. You know what I mean? Cool. If you can remember it like that, same thing. Because we would say, hey, I know here's my angle, and I know the adjacent. So I know that. I don't know the hypotenuse, but I can put this in my calculator. I do know the cosine. So let's rearrange this equation, and we would get the hypotenuse is equal to adjacent divided by cosine of our angle. And we get this. And is that what we would have got from here? Well, hypotenuse cosine of L, we know this and we know cosine. So we would have to rearrange this to find the hypotenuse, which is L over cosine angle. So we get our first equation, you know, for length. This hypotenuse is this initial length divided by cosine of our angle. So if we're saying L is 10, 10 divided by cosine of 38.7. Cool. So 10 divided by cosine of our angle, and we get 12.8. So that is the length of AC. So the length of AC is the hypotenuse is 12.8, you know, let's say inches. Okay, and the length of BC. Length of BC, well, it's just 10 inches. Okay, so now the total length. Length total is equal to length of AC plus length of BC. And that's going to be 12.8 inches plus 10 inches. Now you can see that if we just say, hey, let's use unit length. Length of BC would be 1 inch, and then length of AC would be 1.28 inches. So if you do that, and let's do that. So 1.28 inches plus 1 inch. And we're going to get 2.28 inches is the length total. And back to our first equation. We're basically equating that saying length is weight. So at 38.7 degrees, we're getting a weight of 2.28. Cool. And but now what? You know what I mean? All right, so back at it. So now what? Because cool, we have a weight of 2.28 in that configuration. we already said that if we bring this down to, and remember how we said, hey, we had like a weight of 2 and it cost $200, and then if we had a weight of 3, it cost $300. Well, here you go. This is a weight of 2.28. It's going to cost $228. And if we reduce our angle to nothing, the lowest amount we could pay for this is $200. That would be the weight of the steel. But we wouldn't be able to apply any load, zero load. So we need some sort of angle where the weight is, what angle makes like, let's try 60. So now we're going to use these equations. Our hypotenuse is length over cosine 60. Length is unit length of 1. So 1 divided by cosine 60. Cosine 60 is 0.5. So the hypotenuse is 2. Cool. So yeah, there you go. So just what we know about angles, I can quickly spit out that at 60 degrees, this is going to be 2, length is 1, so we're going to get a length total of 2 plus 1 is 3 inches. And we're going to say, hey, that's equivalent to $300. Okay, and so now we have an equation for what the weight is, and it's kind of a cool thing of just being like, hey, let's turning the weight into a dollar amount, because that's kind of what we want to minimize. We want to minimize the dollar amount, but we still want to get some sort of load out of it. If we only throw in $200, we get zero load. So obviously we have to throw in at least $205, $220, up to $300. But was $300 worth it? That's where we go back to just a little while ago and be like, well, at 60 degrees, we're only getting half. We're only getting half the juice. Okay, so now the next step is to try to get more equations. So we have length of AC is equal to this, and it's related to the cosine, so it's 1, and we're saying this is a length of 1, so it's 1 over cosine theta. Length of BC is just 1. But now we have to relate it to the actual force that we're getting at. So let's write those equations. So we're going to say, hey, the force of AC is equal to P divided by, and it's the vertical component, which is the sine of the angle. So what I just did might be too much, but we already said, hey, this force of AC has to be a large number compared to P. So we take P and divide it by a fraction of 0 to 1, and we get that. And because it's the vertical component, that's the sine of this angle. So there's the vertical component. So we got that one. And then we get the force of BC is equal to the horizontal component of the force of the force in AC. So force of BC is force of AC times the cosine of theta. We want to get it related to this P because that's what we want to maximize. Cool. So force of BC is, hey, let's throw in this into there, and we get P over cosine theta. Sorry, P over sine theta cosine theta. You should recognize that sine over cosine is tangent. So, but we have cosine over sine. So this force of BC is going to be P divided by tangent theta. So there's our other equation. Cool. And let's write our strength equation. Strength is going to be force over area. And let's see, what are we going to do? let's see. I'm going to take a pause. Alright, heck yeah, we're going to start up the clock again. Now, I took about a 2-minute break, and actually, I forget the relationship. It's so subtle that I'm just like, oh, I don't see it. So when I get into that situation, that's why I make these videos, because they're real time, and maybe you can already just kind of understand the relationship and you got it. But how do you go from being stuck to unstuck? Like, that's kind of what I want to put into a video and show. So we're going to kind of go back to this. I mean, we basically had it. Like, we don't know why, but intuitively we're just like, yeah, there is some magic number. Do you want to spend $300 or do you want to spend $200? Do you want to spend $220? It seemed like spending $220 what was the best. You know what I mean? It seemed like somewhere around a 45-degree angle was the best bang for the buck. And we were saying dollars was weight. So we reduced our weight from $300 to $220, and we still get juice. And we know we can't just reduce our weight to $200 because we would just throw our money away. We got $200 worth of material that's totally useless. You know what I mean? So this equation is like, well, how do you quantify usability? Well, it's kind of like, wherever that bang for the buck stops. So what I do is I write out where we're going to say, hey, we're going to put the angles here, and we're going to maybe do 0, 30, 45, 60, 90. And we could even do 15 and 85 if we can squeeze them in. So if we have those angles, now we're going to get the force, and right now we're making everything unit. Unit areas, unit length here of 1, and so we're really just breaking down what's left. So we're going to get the force of AC is going to be is that where I messed up? Well, let's try it. So force of AC related to P, what kind of multiple? So we got 1 divided by sine 0. Well, that's going to be in oh no, this is interesting because just because we have if theta is 0, the force in AC goes to infinity. But that means P. So should we do we rearrange this equation and say P is equal to force of AC sine theta? Oh man, I almost need to get my notes from last night of like what chart did I even do? Yeah, how do you relate it to this equation? Alright, I might take another pause. Alright, hell yeah. So we're back. And man, I had to get my notes from last night. So we solved this last night, and I came to a conclusion that made sense, and it was just like, okay, that was the way to go. But then, starting today on this problem, I got kind of fixated on the idea that, hey, if the cross-sectional area is the same, what's the best bang that we're going to get? And if the angle is 0, we can't take any load. But if the angle is real big, we can only take that max load. We really can't get more than that 58,000 pounds if we're using steel at a 1 square inch area. So then at some point we used that idea to be like, hey, and it's like 20, this length is 20, this length is 1, so we're spending, let's say $2,000. So that was a pretty good way to do it, but still it was kind of hard to be like, well, where is the sweet spot? Is a 45-degree angle where, like, hey, you're no longer getting, like, if we do more of an angle, we're actually getting more weight, but then the force increase that we're getting goes down. So at that point, we increase, for every dollar, we're not getting the same, positive force. But maybe that is the sweet spot, that 45 degrees. But that really, for whatever reason, that didn't prove it to me. And so what we did is we went back and read the problem. And I typically never really read problems all the way through. I read usually the question that they ask. So on this one, I just go right to the question. Determine the angle so that the structure has minimum weight, cool, without exceeding the allowable stresses in the bar. Now, for whatever reason, and we did that. We said, hey, the allowable stress is 58,000 psi if we have, if we're using a square inch of 1 square inch. But then, if we further read, let's read this entire thing, because then we're going to do a separate route that will really flesh out exactly what they're wanting, and we can even get an equation for it. What we're looking for is an equation like this, where we're just like, oh yeah, that's the max, that's where we get the best weight reduction, or probably an equation like this. Hey, best weight reduction, and we're running out, we have like our juice and our pens is just awful. Right there, so we want a graph like that, right, and so that's what we're after. Let's read this. So we have two bars, two bars AB and BC. Whoa, that's a typo. We have two bars AC. So right there's your first typo. We have two bars, AC and BC, of the same material. And catch typos in a textbook. Textbooks have typos, but you got to be careful. Because you got to be like, hey, because even right here it says bar AC. So two bars, AC and BC, bar AC. There you go. So we have bar AC, bar BC. Now the answers in the back of the book typically will be almost 100% right. If you're getting the wrong answers in the back of the book, you're probably just off by a factor of 2 or 4. So definitely check that, or you did something a little bit strange. But even in the back of the book, it can be where there is typos in the back, and that will really mess you up. You'll lose sleep over it, because you'll just be like, I must be right and the textbook must be wrong. But 90% of the time the textbook's right. Okay, so we got these two bars, AC, BC, of the same material, supported by a vertical load P. The length of this horizontal bar is fixed, so we've covered that. But this angle can be varied by moving support A up vertically, changing the length of bar AC. See how it said bar AC again? So this was a typo. To correspond with the new position of the support at A. The allowable stresses, that's in PSI, in the bars are the same in tension and compression. So it's kind of like a material like steel. Cool. That's why we mimicked it like steel. We observe that when the angle is reduced, bar AC becomes shorter. Cool. But the cross-sectional areas of both bars has to increase. Now, let me explain that. Because the cross-sectional, we're using the same material. We're going to the steel yard. Hey, I want the same material. But when we reduce this AC, it can't take that vertical load. We showed that. That component in the vertical direction is real small, can't take that load that we're designing it for. So the only way to take that load is to take this bar, maybe with a width of 1 inch, and for the love of God, I might have to drive to Walmart to get more pens. I will definitely let you know if I do that. Okay, yeah, I think we're gonna go to Walmart, get more pens, because we're into this. We're deeply into this problem. All right, catch you on the flip side. All right, heck yeah. So let's get after it, and let's use that new piece of information. So it is asking that we observe that the angle When the angle is reduced, bar AC becomes shorter, but the cross-sectional area of both bars have to increase. I mean, it should just say the cross-sectional area of bar AC has to increase if this angle, because, you know what I mean, if this angle goes to 0, AC has no vertical component, very little vertical component to take whatever load that we're putting in here. And if we're saying still, maybe we do want to carry a 58,000 pound load. And so the only way to carry that is to make this member thicker. So let's draw that in. And then so here's the cross-sectional area of 1 inch, but the thickness has to increase. So this thickness definitely has to increase. So now the area of this is, let's say, this 1 inch, and that pen's dead, 1 inch times the thickness. Cool. So let's and because we're buying both material has to be the same. This bar and this bar has to be the same material. So that's why it says when we reduce bar AC, the cross-sectional areas of both bars increase. And that's going to increase the cost. Cool. Because the axial forces are larger. The opposite effect occurs if the angle theta increases. Okay, so when we go this way, you know what I mean, we can decrease the thickness. But we can only decrease the thickness back to 1 inch. You know what I mean? So this thickness will vary between 1 inch and infinitely thick. If AC is at a almost 0 degree angle, this thickness has to be infinitely thick to actually support the load of 58,000. And then if the angle goes to infinity, or I mean, sorry, 90. If the angle goes to like almost 90, this bar becomes infinitely long, but still the cross-sectional area has to be, the thickness has to still be 1 inch, because we have to get a cross-sectional area of 1 total to support this 58,000, because the strength of steel is 58,000 pounds per inch squared. Okay, so that relationship is what's going to give us, you know, some sort of curve this way and a minimum. Okay, so let's keep reading on. Thus we see that the weight of the structure, which is proportional to the volume, depends on the angle. Sure, so for whatever angle we pick, we're going to have the weight. So if we go a 0 angle, we have infinite weight. It requires infinite weight. If we go to a 90 degree angle, it's going to require an infinite weight, because this bar is so perfect. So just right there, I do a lot of math problems where, especially if you can kind of pick two values and they both miss the mark, but then there's an answer in between, you know what I mean? Then you're money. You know what I mean? So like any, let's say we do y is equal to x squared minus 1. Let's say we don't know what that is. You know, we don't know the solution to it, so we just choose 4. So we go 4 squared minus 1 is 16 minus 1, that's 15. Cool. Now I'm going to do like, now I'm going to do 0, throw in 0. So I'm going to go 0 squared minus 1 is equal to negative 1. Well, cool. Then I know I got a positive 15 and a negative 1. So I know, and I chose x equals 4 and x equals 0. So I know that in between x equals 4 and x equals 0, there's going to be a number that crosses 0. There's going to be a number in there that's 0, because this is a linear function, you know what I mean? And so if we have a positive and a negative, there's going to be some number that crosses the 0. You know what I mean? If those are the two values that we got. So the same thing for this. If we're saying that the angle is 90, we're going to have infinite weight at theta equals 90. If the angle is 0 degrees, we're going to have infinite weight. And we know that if the angle is 45, we're not going to have infinite weight. You know, we're going to have like a weight of, again, like 3. That's, you know, of unit values 3. So obviously, so if we did a graph, we would say, hey, angle, so x is your theta, and then this is your weight of the structure. So 0 to 90, you have infinite weight here, infinite weight here. Well, perfect. I mean, this is your classic where the structure has to weigh something. The structure can't weigh nothing. You know what I mean? And so like we said, if we throw that $200 at it, the structure is going to have like a weight of unit 2. So there you go. And if we angle to 0, our weight's going to go up to infinity. And so there you go. And this is if any time that you have like an x squared, especially if you have an x squared, even this one, we know a couple things about this x squared graph. If we said, so let's graph this. So we said x is 1, 2, 3, 4, and we got up to 15. So we're going to do 5, 10, 15. So there you go. And we said x is 0, and we got -1. So 5, 10, -50. So we got there. So even like right here, we know a couple things. And let's throw in x is equal to -4. Well, that's going to be 16, again, minus 1. That's going to be 15. So if we go 1, 2, 3, 4, -4, hey, we're back up to 15. And if we know we have an x squared, and we have two terms that are basically at the same height, we know we're going to get a dip in between. So we pick a value in between and we see one down there. So we just know that we're going to get a parabola like that. And so the same thing with this equation. We know at 0 we're going to all the way up to infinity, at 90 all the way up into infinity, and we know that somewhere in between it has some sort of normal amount of weight. Cool. Then you're going to get a relationship that does that. So now we actually have a relationship. Oh, sweet. I'm glad I caught that. So I got to set my timer for every 10 minutes just to make sure I have the crispest. I'm filming this with the DSLR, and so we're trying to get the best focus, you know what I mean? And so there you go. So we only have 10 minutes on the clock. I caught it at 8, though. I just forgot to set my timer. Okay, so now we're just going to be continuing right along. But yeah, now we have this relationship that we're shooting for. Cool. So now how do we set this up? I don't know. I think we can go back to the fact that we can choose 58,000 pounds for our P. But now we're going to adjust our angle and know that when we adjust our angle, this affects the thickness. Because if we have 58,000, only at an infinite angle, or at an angle of 90, when AC is infinitely long, will the force in AC be 58,000. So only then will our thickness be 1. Cool. So let's just pick some, and we're going to. So I'm going to go here. I'm going to go theta is 0, 30, 45, 60, 90. Now these problems, I don't mind spending hours, just kind of working through them. My goal is not to get to the solution. My goal is to work through all the kinks in my habits so I can develop better habits. To be like, oh, I recognize a pattern here. Infinite weight, and then a weight in between. So obviously there's going to be a Goldilocks moment, and we're going to get an equation that's going to have a parabolic, or at least a minimum. You know what I mean? It might not be an x squared equation because we're dealing with sines and cosines. Okay, so let's choose this 30 degrees. So at 30 degrees, here's our component. And we're going to say that P is 58,000. So the force, so let's just go here. Force in AC is going to be, or the force in AC sine of the theta is going to be equal to this vertical component, which is P. Cool. So now we can find the force in AC is going to be P divided by sine theta. So right now, I'm going to obviously know I'm going to get a bigger number. Right now is where I want to go to my strength equation. Strength is force divided by area. So now I know this force is going to be Fc, but what I want, and I know I want this width to always be 1. Just so we're just messing with the thickness, just one parameter. So this I'm going to call I don't know. What should we call this? Should we call it a W? I don't want to confuse it with the weight. So we have a thickness. I'm going to call this B. Yeah, dimension B. So the force over area is going to be force over B times the thickness. And B is 1. So I can just put a 1 here. So force is over 1 times T. Cool. And I know that this is force AC. So force AC... and I know the strength of my steel is 58,000 pounds per inch squared. Cool. So now I can figure out the I can rearrange for thickness. So thickness, let's bring T upstairs. The stress downstairs is FAC divided by 1, and then this 58,000. So cool. So even in this config... Oh, and then FAC is equal to P divided by sine theta. So I got that 1, I got that stress, and then sine theta. And never get confused. You shouldn't be able to get confused with your sines and cosines because, yeah, it's whatever this component is, here's your angle, sun is shining on the sine end, the vertical component's only going to be 50% of the horizontal. So this number is 0.5, it's 50%. But now if we want to solve for FAC, we take the force and divide it by 50%, that means that this has to be twice. So if I have a 30 degrees, the force here if I want to capture if P is 58,000 pounds and I have 30 degrees, the force in this member is going to be twice that. It's going to be 116,000 pounds. And I know that steel can only take a stress of 58,000 pounds per square inch. So I have a force over area, 116,000 pounds divided by, and I know that has to be 58,000 psi or pounds per square inch. So I need 2 square inches. Cool. And I know my my width. I'm going to say the width is B is 1. And so my thickness has to be 2. So at the end of the day, that's what this equation means. So even though it says P 58,000 psi sine theta and theta is 30, it should just be real easy to see that this thickness is 2. So let's do that. So we have P is 58,000 pounds. That's what we want to. That's the load that we want to capture. Steel has a strength of 58,000 pounds per inches squared, and sine of 30 is 0.5. There you go. So pounds cancel, inches squared goes to the top. This is 1 inch, you know what I mean, the width. So it cancels one of those inches. So inches goes to the top, which will be the units on thickness. Dividing by 0.5, that's like dividing by 1/2. Dividing by a fraction is the same thing as multiplying by the opposite, inverse of the fraction. So now we multiply by 2. So there you go. That's where we get that doubled up. And so we have 58,000 divided by 58,000. That's 1 multiplied by 2. So our thickness right here is 2 inches. So cool. So now we have like, hey, our thickness at 30 degrees is going to, we have to have a minimum thickness of 2 inches. Now we have to do a check on reality because, hey, if we at 30 degrees, the force in this member is 116. But let's check the force in BC. Because if we have the force in BC, well, let's see if that gets a little crazy. And the force in BC is just the horizontal component of the force in AC. So if the force in AC was 116, the horizontal component is just cosine of the 30. And that's going to be 0.866. Cool. This horizontal component will always be a cosine of whatever AC is. So, this is where you can kind of use like, okay, let me just spell it out, is that the force in this member will always be less than if we have 2 inches here, this member is just good to go. It's always a check mark on BC. There's no configuration. I don't think so. Let's reduce theta to 5 and see if anything weird happens, but I don't think so. I think the member AC is going to get astronomically, that thickness is going to get really huge, but the force in BC is always the horizontal component. So whatever AC is, the force in BC is just the horizontal component. Now, in engineering, in physics, this is a huge topic of like Pythagorean's theorem. We're always usually solving for like the force vector, at an angle, and we can resolve it into the horizontal and vertical components. Well, in a three-dimensional world, these horizontal components will always be less than, or in the case of theta being 0 degrees or 90 degrees, they either be less than or equal to your original horizontal. So let's say they are equal. Let's say we found the thickness. We know that member AC needs to be 2 inches thick. Well, cool, because it has to take that load. Well, the horizontal component, even if the angle is 0, it just means that, hey, this member BC has to be 2 inches thick in that case. And if this goes this direction, it means that, hey, this doesn't have to be thick at all. So there you go. That's a fundamental principle of engineering is, the vector is usually always the hypotenuse, and the horizontal components and vertical components are always less than. That's such a mind-blowing thing of just like, hey, now I have a thorough understanding of what sines and cosines are. Because the hypotenuse, this is the hypotenuse times the cosine. This is the hypotenuse times the sine. Sine and cosine are always less than 1, or 0 or 1. You know what I mean? Unless you're getting into particle physics, you don't need to know that sine is -1 to 1. You know what I mean? In a three-dimensional world that actually, you don't measure negative distances, all you have to do is remember that sine and cosine is a percentage between 0 and 100%. It's a percentage of that horizontal. So there you go. So there's a proof that we can just put it to bed that for whatever thickness that we need this member AC, we can just be assured that, and then let's go back to the problem. If we figure out what thickness we need member AC, we're going to buy that same material at the steel yard for both members. You know what I mean? And then member BC is just overly built. Let's throw another check mark. But that's where this problem comes. It's like, hey, we need to design for member AC, and we need to find its thickness. But once we do that, we're going to buy that same material for both pieces of this project. Okay, so now that we have that, and we chose that 30 degrees meant that we had a thickness of 2 inches. So and we thoroughly hashed out that we're good to go on this member. So then the next part I guess the only other part of this equation right here is that we need to figure out what the total weight. If we chose 30 degrees, we said our width was 1 inch. And now we found our thickness for both members is 2 inches. And now we know and then we should know the lengths of both members. This is L, this is LAC. This is length of BC. Then we should be able to figure out the weight, because the weight is equal to the volume times the weight density. Volume is area times length. Area is that B, that width, unit length, times the thickness times the length, and then times the weight density. So here's the volume, here's pounds per volume. Cool. And so now the weight of member AC. The weight of member AC is going to be the thickness of member AC, and the width, thickness, length of AC, unit length. The weight of BC is going to be the width of BC, thickness of BC, length of BC, unit weight. Cool. And then the weight total is equal to the weight of member AC plus the weight of member BC. Cool. And so the weight total is going to be both these added. And now let's figure out if theta is 30, what's the length of AC and what's the length of BC? Length of BC doesn't change. Its unit length is, let's just say 1. So now we are just going to use unit length. Even though this is nonsensical, having this just be 1 inch, we're just going to, all we want to be concerned about is unit lengths. So there you go. So length, if this is 1, this length is going to, and if this is angle 30, what we know is we know what the cosine part is. We don't know what the hypotenuse is. You know, so if you go back to that middle school trigonometry, you're going to say cosine of my angle is adjacent over hypotenuse. I want to know the hypotenuse. I'm going to go hypotenuse is equal. So I'm going to rearrange this equation upstairs, downstairs. And I'm going to say hypotenuse is adjacent divided by cosine of 30. I know what adjacent is. That's 1. So 1 divided by cosine of 30. Cool. So now I have an equation for the length AC. Length AC is going to be 1 divided by the cosine of the angle. So I'm going to go... we could do this. Yeah, we could. Length AC is 1 divided by cosine of the angle. And so I'll do that in my calculator. 1 divided by cosine 30. And we get 1.15. Okay, but that's just the length. And we need to find the weight. So the weight is going to be, the weight of AC is going to be length times thickness. So we got to multiply by 2. So we got a thickness of 2. See, this is the thickness right there. And so we're going to get 2.31. Cool. Now we would need the length of BC. Well, we know this is unit length of 1. So now the weight of BC is 2, because we have a thickness of 2. So now the total weight is adding both of these. And we're going to get 4.31. Okay, so that's the first one we did. We'll probably get a fresh sheet of paper to make our chart better. But I think we hashed out exactly what we need to do. And maybe we'll just keep on this so you have all the information. I don't mind writing small, and I think you get it. And so yeah, so right now we have a weight of 4.31. Again, at 0 degrees we have an infinite weight. And at 90, we have an infinite weight. So we can already say infinite, infinite, and here we go, 30, 60, 90. So at 30 degrees, we have a, and we're going to say, at 30 degrees, we're going to have a weight of 4, so we're going to have a, I don't know, let's just go 1, 2, 3, 4. So there you go, 30 degrees 4. Like, don't pay attention to that graph because we're going to make a new one. Okay, so there's our first point. Let's go to 60. At 60 degrees, hey, now we're basically able to capture that 58. Remember if we have 60 degrees, it's almost capturing, AC can pretty much take the entire weight. So remember that AC could be about 50,000. And the reason for that is the vertical component, the sine component. Sine of 60 is 0.866. It's always a good one to memorize, 86%. And if you're just guesstimating, that's basically 100%. you know, that's why I'm just like, hey, the force in there at a 60-degree angle is basically about 58,000. It's 50,000. And so how do we get that number? Well, we would take the force P, 58,000, and now we're going to, oh, no. No, I apologize. If P is 58,000, if the horizontal component is 58,000, again, back to Pythagorean's theorem, the hypotenuse has to be more than 58,000. So the hypotenuse, we're just going to have to guess, let's say it's 65. 65,000, the horizontal component is 58. Cool, so how do we get that? This is the sine part, so we're probably going to do P sine theta. You know what I mean? We're going to take sine of 60, which is 0.866, and we're going to take that 58,000 pounds divided by 0.866. Dividing by a small number gets that bigger number. Cool. So 58,000 divided by sine of 60, and we get 66,000. So we get that 66,972. And remember, so how does this relate to that 30 degrees? At 30 degrees, we had to double. The force in here is 116. At 60 degrees, hey, the force in here is only 66. The strength of steel is 58,000 pounds per square inch. Our equation is sigma force over area. And so to get the area, we rearrange the equation and say area is force over sigma. And so we're going to go this 66,000 divided by 58. And so divided by 58,000 is 1.15. If you remember, I mean, that's going to be the area in square inches. So the area in inches squared is 1.15. But remember, I chose B for our width to be 1. And so basically our thickness is just this number. So cool, our thickness is 1.15. If our thickness is 1.15, for member AC, that we bought the same material at the steel yard, so our thickness for BC is going to be 1.15. Alright, heck yeah, got a new battery in, and back at it. Okay, so we found the thickness is 1.15 for member AC, and we bought the same steel at the steel yard, so the thickness of BC is going to be 1.15 as well. And we already did a check on reality that BC will be plenty strong in compression. That's never an issue. Never an issue on that one. Okay, so now we just need to figure out the weight again. The length of AC is going, at 60 degrees, is going to be, well, this 1 is going to be, and this is the cosine, so what is it? 1 divided by the cosine of 60. Cosine of 60 is same thing as sine 30. And I know that's 0.5, so 1 divided by 0.5, that's 1 divided by a half. 1 divided by a fraction is multiplying by the, so we get 2. And that makes sense. At 60 degrees, this thing is going to be twice. Holy Toledo, we're already running out of light. Alright, so, okay, so we have a length of 2. So length of AC is 2. Length of BC is always 1. So we have a total length of 3. So length total is 3. And that's essentially going to be the weight. So what did we say here? Yeah, thickness of 2 for this one. Oh, yeah, at 30 degrees, this length is only 1.15. I'm going to double check that. 1 divided by cosine 30 is 1.15. Yeah, 1 divided by cosine 60 is 2. You know what I mean? So there you go. Length of AC is 2 right here. Length of AC is 1.15. Length of BC is always 1. Holy Toledo. So we got this kind of messed up. So the length of BC is always 1, but the weight, the weight of BC. Yeah, the weight of BC is 2. So I'm going to square the weights. There you go. So now we have the length of AC is 2, but the weight is going to be that factor. The thickness was going to be 0.115. So we have 2, and I got to store that as x. in my calculator. Stored as x. So we have 2 times that. So now we have a weight of LAC as 2.3. The weight of LBC, because it only has a length of 1, is going to be that 1.15. And then so plus x. So now we have a total weight of 3.46. Okay, so at 30 degrees we had a weight of 4, and I'll double circle this one. So double circle this. So at 30 degrees we had a weight of 4.3, and at 60 degrees we have a weight of 3.6. So there you go. Infinite, 4, 3. So obviously we're going to come down through here and get to some minimum. You know what I mean? And so now let's do 45 and see where we are on that. And again, but no, let's go back and do 5 degrees. You know, just to show that the thickness blows up. Because if we have this really narrow 5 degrees, the vertical component is the only thing that can take this 58,000. And the vertical component's real small. Vertical component is the sine component of the angle. And so we, and we're trying to find the force in this member. So the force in this member is going, and we're saying the horizontal component right here has to be 58,000 because that's the only thing that can hold up this 58,000. Force of AC has to be this 58,000. Holy Toledo. Alright, we might be running out of light and we probably have to charge some more batteries. Oh, my battery charger is totally not charging. Okay, there we go. Now it's charging up. It was unplugged. Okay, so we have to take that 58,000 and we got to divide it by, so we're dealing with the sine of the angle. You know what I mean? Sine of 5. And sine of 5, that's going to be that 0.077%. So sine of 5 is 0.087, about 8.7%. So 58 divided by sine of 5, or 58,000 divided by sine of 5. Alright, I definitely need to get more batteries. Catch on the flip side. Alright, heck yeah. Now this is perfect. Got a new battery, got new light, and I'm not going to grab a new sheet of paper until we actually get this 5 and 40 done. Because, you know, the fact that we can't write things down really helps us intuit what we're doing. So we were trying to find the force in AC. If the angle is real small, our vertical component is the only thing that can capture this 58,000. So this vertical component has to be 58,000. We use Pythagorean's theorem that shows, hey, if we have an angle like this, if this is 58,000, this has to be huge. You know what I mean? And then so, because this is, this has to be huge. And if this is our angle, this is our sine component. So then we say, hey, this right here, this length, or this force in AC has to be that 58,000 divided by a small number, and we're dealing with the sine of the angle. So sine of 5. That's literally how, you know, intuitively you can actually get the hypotenuse. You can be like, okay, I'm dealing with a vertical component, which is a sine component, and I want to find the hypotenuse. It has to be bigger, so I have to divide by a smaller number. Sines and cosines are those smaller numbers. And because the angle we're dealing with is here, sun is shining, this is the sine component. If we knew this component, you know, let's say it was like 300,000, then we would say 300,000 divided by cosine of 5 degrees would be this. But look, if this is 300,000, this would be like 301,000. You know, these lengths are the same, but it is smaller. Like I said, three-dimensional objects. If you know one of the orthogonal sides, that's what these are called, orthogonal, because they're perpendicular to each other. If you know one of the orthogonal components and you're trying to find the hypotenuse is always going to be bigger. So you're always going to divide by a smaller number, which is sines and cosines. And depending on which angle you use, draw the sun is shining. This is the sine component. The angle is shining on the sine component. And then this other side is the cosine. All right, so back to it. 58,000 divided by sine of 5 gives me that hypotenuse, that force in AC. So, and we just did it. Yeah, it's a huge number. It's 665,475. But now we just know intuitively that force, this is in pounds, force divided by the area, I apologize. Well, let's go back to our equation. Strength is force over area. We want to know area, so we rearrange it. Area equals force over the strength. So we need a force of 665,000. We're going to divide it by the strength of steel, which is 5,800 pounds per square inch. And we're going to divide this by 58,000. Okay, so we get 11.47. So that's going to be the thickness, because the area has to be 11.47 inches squared. We're saying the width is 1 inch. So the only thing that can actually get that area is the thickness. So 1 times 11.47 is 11.47 inches squared. 1 inch times 11.47 inches of thickness is a unit of area of 11.47 inches squared. Cool. So at 5 degrees, we're going to have a thickness of 11.47 inches. That means that our weight is going to be so weight of AC, if we go back to one of our equations, is going to be the width, is going to be, well, it's the area times length times weight density, which is width times thickness times length. We know the width is 1, thickness is 11.47, so it's going to be 11.47 times that length. And at 5 degrees, basically the length is just the same. The length is almost, length of BC is 1, so the length of AC is basically 1. So at the end of the day, we can say maybe like, hey, the weight is really close to 11.47 for member AC, and since we bought the steel at the same steel yard and has a thickness of 11.47, this has a length of 1 but a thickness of 11.42, so the weight of BC is also 11.47. So we can just kind of really easy guesstimate that this is going to be 22. So at 5 degrees, so 30, 15, 5. We're already going to be up to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're already off the charts, right there. So there you go. So at 5 degrees, our weight is like 20 pounds of steel. Just ridiculous. And if you think about it, we're using a unit length of 1 inch. So if we're using a unit length of 10 inches, this is 100. So it would be like 100 pounds. So right here we have like 100. So at theta is 5 inches. We have like 100 pounds of steel, or 220 pounds of steel. But we can actually, we only need like 3.47 pounds if we did 60 degrees. Cool. So now that we did that, let's find the magic number, which is this 45. I mean, just by observation. And then we'll do the fresh sheet of paper and do the full equation, derive it. Because essentially what you're going to do is you want to get an equation for this line, and then you want where the slope is 0, right at the bottom is the magical part. And so you would have to do a derivation of that equation, and when the derivative of the equation is equal to 0, when the slope is equal to 0, which is just the derivative of the equation with respect to theta, is 0, that's going to be the point, you know what I mean? That's the answer. That would be the angle where the weight is minimum for the strength that you're trying to achieve out of it. Okay, let's do the 45, and I think we have a thorough understanding of this. We want to capture this 58,000 pounds with this structure. It has a vertical component that can only be taken by this member. But the member is at a horizontal. So 58,000 divided, and here's our angle of 45. This is the sine component. 58,000 divided by the sine of 45. And sine of 45 is 0.707. So 58,000 divided by sine 45, and we get 82,000 pounds. Cool. We're going to divide that by 58,000 pounds per inch squared. Inches goes to the top, and now we have the inches required in this member, the thickness of this member. So divided by 58,000. This is the area, basically, 1.41 inches squared, but we know we have a width of 1, so thickness is 1.4. So 1.41, which is basically the square root of 2. And now we need to find the length of AC. Well, I mean, just by geometry, if this length is 1 and we got a 45-degree angle, this length is 1. 1 squared plus 1 squared, square root of that is square root of 2. So we already know that the length is 1.41 as well. Square root of 2 times square root of 2, well, that's a weight of 2. So member AC has a weight of 2. Member BC has a length of 1 and a thickness of 1.41. So now we got a weight of 1.41. See, and you might not, even mentally, you might not be able to keep up with where my mind's going, but just the fact that I'm just showing that if you hash through, definitely set up 1, 2, 3, 4, 5 scenarios, and if you hash them through, it's just such a good way to demonstrate your knowledge of what the sines and cosines, what the components are, how they relate to the hypotenuse, how the hypotenuse is your force vectors, and in this case also your hypotenuse is length. So that's a very statics related thing, is that your hypotenuses, your members at angles are one also lengths, due to sines and cosines, but there's forces involved too, which is very synonymous with forces at angles. So there you go. Okay, so what did we get for our weight? Because it's 2 plus 1.41, so we get a weight of 3.41. Is that the lowest number? We had 3.46 for 60 degrees. Oh, so that's interesting. You know what I mean? So that this, once we, hopefully I didn't make a mistake there. But yeah, 3.41 is our lowest number so far. Alright, heck yeah. So now we get a fresh sheet of paper, and what we're going to do is, if we were that math wizard, they could just read this problem and go right to the equation and see that we could take the derivation of that equation. We would just be money honey. But I don't think anyone's that smart, and you should get used to just throwing out a scenario and then throwing out the scenarios on either side of that, seeing what the correlations are, and then seeing if you can actually... So we started this problem by saying like, whoa, yeah, there is a bang for the buck. And then we figured out, oh, no, if the way we read the problem, if we size up the member, sure, we have to get, we would have infinite weight at 0 degrees and 90 degrees. So then there's some point in between that's just going to be perfect. And sometimes... Now, this isn't typically what you would do, but especially when they're like, hey, what's the weight? Well, we can be like, hey, the weight total. Like that's the first equation that if you're just a genius, you can be like, oh, okay, they're just asking for the total weight. Well, that's going to be the length of AC times the area of AC times the weight density, plus the length of member BC times the area of BC times the unit density. And then in here it says you're buying the steel at the steel yard, that's going to be the same. So area of AC is equal to area of BC, which is just area. And then that's where I do something creative and be like, hey, well, let's say this has a width of B, and we're just going to set that at 1 inch. So now area is B times T, and B is 1 inch, and thickness is T. So now we can just say, hey, area is just very synonymous with T. So our weight total is going to be the length of AC times T, unit density, plus the length of BC times T unit density. And if we get more creative, we can just be like, hey, unit density is a constant, the thickness will change, and the length will change. Because if we change the angle, so there you go. Now we have a relationship. So we want to change the angle, and the length is going to change, and the thickness is going to change. Because this is a constant, we can just get rid of it, and we can simplify this equation and then bring out the T. And so thickness times length of C plus length of B, that's our relationship. So this weight, because now if theta is 0 degrees, let's go to 90. If theta is 90, with this equation alone, our length of AC is infinite. So we have infinity for this one plus 1, infinity plus 1, times the thickness. So now we have to bring in that equation. Like, what is thickness related to? Well, thickness we said was related to area, and then that's where we have to bring this equation for strength. Strength is force over area. So now we're trying to, solve for area, and we're going to say that area is area is force over strength. Oh, this is where I'm losing my mind, though. This is probably the hardest part of the correlation, and that's why we went back and did it. 'Cause it's like I'm losing it here, and it's just kind of interesting why I'm losing that. Kind of just that feel for it. And area is synonymous with T, so we basically have T is equal to force over sigma. Okay, and this is where we have to choose some P. So we have to choose some P that we're trying to design for, and now we're going to say, well, the force in AC, like the force right here. So the force in member AC, sigma, is going to dictate the thickness of member AC. You know what I mean? Cool. And then the force in member BC over sigma might dictate the thickness in BC. Now, we're not going to concern ourselves with the force at BC, because we already determined this is always going to be less. Force of BC is always going to be less than the force at AC. So we can just cross that one out, and now we just have to solve for the force at AC given some P. So if we give this P, this member AC has a vertical component and then a horizontal component that can capture it. The vertical component, it is P. There you go. So the force in AC, and again, now we have a good understanding. With theta, this is the sine component. Force in AC is going to be that P divided by sine theta. This is always a fraction of 1, and it's always a smaller number, so the force in AC is going to be bigger than P. Cool. So now we can put this into this calculation. So we have thickness of AC is going to be P over sine theta, and then that stress allowable. Okay, but at the end of the day, again, we have two things that are constant. We're going to say the design P is constant. You know what I mean? And we're going to say that the design strength allowable, sigma allowable, given that this is your equation, strength is force over area, is also a constant. So we can really say thickness AC is 1 over sine theta. Cool. So now we can actually, and then now we can by area of AC is equal to area BC. We bought the steel at the steel yard. Thickness of AC is 1 over sine theta. Thickness of member BC is also just 1 over sine theta. Thickness of BC is equal to thickness of AC. Cool. So now, and that's this equation, you know what I mean? The weight total is basically just going to be the thickness of AC. We're designing for that. And so let's use that weight total equation. Weight total is going to be 1 over sine theta because that gives us the thickness of AC. But now we need to find the length of AC. The length of AC is going to be, well, we know the length of BC, it's 1. And now we already talked about how Pythagorean theorem says, hey, if we know the orthogonal component, we know that the horizontal, or the hypotenuse component is going to be greater than any of the orthogonal components. So if we have 1, what do we divide it? We're going to divide it by a sine or a cosine, because we know that those are numbers between 0 and 1. They're numbers that are less than 1. That's all we need to concern ourselves with, because we're trying to get this bigger number. We know if this is the angle we're using, sun is shining on the sine part. This is the sine part. That means this is the cosine part. We have information about the cosine part. You know what I mean? So just the quick way to get here real fast is be like, okay, I'm going to take the cosine part, 1, and I'm going to divide it by the cosine of the angle. And that's going to be the length. Length of AC is 1 divided by cosine theta. Cool. And length of BC is 1. So at the end of the day, that plays. Because let's try one. Cosine 60 is 0.5. 1 divided by 0.5 is 2. And that's going to be the length of AC. We've already done that. So right here, we have fully established an equation for the weight of, this is the simplest proportional, hey, if I change theta, this is how the weight changes. This is as mathematical as it gets. If we want to throw back in the P's and the allowable stress, you bring this equation in. You know what I mean? The thickness. So we can do that. Weight total is going to be P over sine theta, and then this stress allowable. So there you go. That's going to be that component. And then we're going to say, and does that get it done? Does that get it done? Yep, because P over sigma, because they're constants, they show up here. Alright, heck yeah, home stretch. You know what I mean? So what we did is we came up with just a really nice mathematical equation that relates the weight due to the sine of theta. You know what I mean? This relationship will give us an equation where your weight is going to be infinite at theta is equal to 0 and theta is equal to 90. And then it's going to have some minimum. So we could just go graph that right now and then find the minimum and call it a day. But we need to go back and be like, well, let's say I do want to throw that P 58,000 in for P, and I do want to throw stress allowable for steel to be 58,000 pounds per square inch. And then I want to get an equation for that shows, hey, I want to throw in my calculator a value of the angle, and I want it to churn out the weight in pounds. You know what I mean? Because I want to throw in the fact that the weight density of steel is 0.29 pounds per square inch. You know what I mean? I want that equation. I want the official equation to explain, you know what I mean, what's going on. And so we have to, so I started here by saying, oh, well, this 1 over sine theta was just the relationship between this thickness. You know what I mean? See how thickness is, so we have weight is thickness times the two lengths. And the thickness of AC is related to the P over sine theta stress allowable. So, I went to go put that in, and then I was just like, well, how does that show up in these two components? So then I had to go back and be like, okay, let's re-talk about this. So we have let's see if I can actually talk my way through this. So we know that if we design for like a P of like 58,000, we need to find the force in AC, okay? And again, if this is 58,000, only the vertical component of this member can take that load. So that means the load in this member AC has to be bigger, Here's our angle. What we know is the vertical component's got to be 58,000. So the angle, the sun is shining on the sine end. We know the sine part. So I mean, you can go back to the 8th grade method of saying, well, sine theta is equal to opposite over hypotenuse. Does that get the job done? Because I know what the opposite is. I don't know what the hypotenuse is, but I know I want the angle of like 30 or whatever. So that does get the job done. Or you could write cosine is adjacent over hypotenuse, but we don't know the adjacent. You know what I mean? And that's not what we're worried about. We want if P is 58,000, only the vertical component of this AC can take that. Because remember, BC has no vertical component. Its ability to take a vertical load is none. Cool. All right. So that's where you can quickly go from P design divided by sine of the angle. Gives us the force of AC. Cool. That's where we get that. So once we get the force of AC, then we go straight to the strength equation. Strength is force over area. Cool. Well, we know what the force of AC is. What are we trying to find here? We're trying to find the area. Because we're trying to go buy steel at the steel yard, and we need to know what cross-sectional area we need. Cool. So we rearrange this equation for area, so we get force over the strength of steel. And now we're going to get force AC over sigma, and that's going to be P sine theta sigma. Cool. That's exactly what we had here, P sine theta over sigma. But now, at this point, we said, cool, and I just want, for aesthetics, I only want this to be 1 square inch. The areas can be whatever they want to be, but I just, for aesthetics, I want this to be 1 square inch. So now I know my thickness, because area is going to be B times thickness. B is 1 inch, and I know that the area is going to be P divided by sine theta times the strength of steel is equal to BT, which is 1 times thickness. So now I have an equation for my thickness. That's how I get the thickness of member AC is just P over sine theta. So yeah. There you go. It's the same thing. So this is the thickness of A. It's also the force of member AC is just P over sine theta. The thickness is P over sine theta with the strength of steel. This is the normal tensile strength. The normal tensile stress, the tensile strength of steel, or however you call it. I just say strength of steel. It's just so much easier. My mind doesn't melt. It's in units of PSI. But there you go. We get the thickness. So now the bread and butter of this is like, well, don't we need to figure out the thickness of member BC? Sure, because we have a force in AC that's related to P over sine theta. So this is actually going to be pretty big. Force of AC can be real big. And if theta is 0, if we bring this down to here, this force in AC goes to infinity. You know what I mean? So what does BC do? Well, let's take the opposite. When theta is 90, this member just goes really, really high, and the force, well, the force is just P. You know what I mean? If this has, if it's just totally vertical, it's the same thing as hanging a member from a ceiling. You know what I mean? So then the force in the member is P, because sine of 90 is 1. So then you have P over 1, and you have 1. So at 90, the force of AC is 1. So what we need to do, let's take that consideration. If this theta goes to 90, what's the force in BC? Is it doing anything? You know what I mean? If we're taking all this load here and then we just have another member come up and touch it, it's not doing anything. So that's where we need to write the relationship between the force of AC and the force of B. So let's just take let's take 30 though. Let's take an angle of 30, and the force in AC now that we're stellar with this, is just P over sine theta, which is P over sine 30, which is P over 0.5, which is basically 2P. Cool. So now the force in AC is twice the design load that we're trying to carry. But now the question is, what's the force in member BC? Well, just like using Pythagorean's theorem, we said this was 2, 1, 2. This is 1, length of 1. You know what I mean? So now we want to know what this is. Well, if we said the force of AC is 2, then the force of BC, just by looking at Pythagorean's dimensions, the force of BC is 1. And it's less. At the end of the day, we just know force of BC is less than force of AC at an angle of 30 degrees. Now we just need to check it for all angles. Oh. And I don't think I was right on that. How did I mess up? Well, let's get the force of. Oh no! Shoot. Oh, my bad. Because I was going. Yeah. Two different things going on here. Okay, so if we do take an angle of 30. This horizontal component is only 50%. Sine of 30 is 0.5. So if this has to be P, the reaction in here has to be 2P. So that's force of AC is equal to P over sine theta. We already did that. That's P over sine 30. P over 0.5. That's 2P. So now we know that the force in here is 2P. But now we want to know the horizontal component. And just visually, I always recognize that, a 30-degree angle, well, yeah, sure, this is half, you know what I mean? But this is equivalent to 100%. Like, this is 50%, sure, we all know that. But just think, from a guesstimation standpoint, the cosine component of a 30 degrees is closer to 100% than it is to kind of any other number. And the cosine of 30 is 0.866, so it's 86.6%. But that's where I messed up that. So if the force in this member is 2, what's the adjacent component, the horizontal component? Well, that's where we get this 1.3. That's where we say, hey, the force of BC is taking that hypotenuse, force of AC, times the cosine of the angle. So we have force of AC. All right, hell yeah, more time on the clock. So force in BC is force of AC cosine of 30. Cosine of 30 is 0.866. And now we have force of BC is equal to force of AC times 0.86. 86% of force of AC. But we have to go back to our equation. What is the equation for force of AC? Well, it's force of AC, again, just real fast. It's the vertical component of P, or the vertical component P. P is in the vertical direction. AC has a vertical component, and that's the only component that can take this force. So that means the force in AC must be larger than P, and we get that by saying P divided by sine theta. So cool. So this force AC is P divided by sine theta. But we're saying, let's go back to this equation. Force of BC, yeah, it's just the hypotenuse times cosine of the angle. But we're saying this force of AC is P sine theta. So now we can say the force of BC, putting this into here, is P divided by sine theta. That's the part that we put into there, times cosine theta. And just from the engineering perspective, you just have to know that tangent is sine over cosine, is opposite over adjacent. Just that just has to be, you just spit out of your head just instantaneously. So then whenever you see a sine theta over cosine theta, you can just instantly say, hey, that's tangent theta. But if you see cosine theta over sine theta, that's just 1 over tangent theta, because then the sine's on the bottom, cosine's on the top. So we definitely see that force of BC is P over tangent theta. All right, hell yeah. And that's the equation. That's the equation for the force at BC. So now we're going to go up here. We have the force of AC and then the force of BC. So now we've been doing this so much, we know that the force of AC is P over sine theta. And at the end of the day, we know exactly what this means. You know what I mean? We know we're dividing by a fraction smaller than 1. This number is a number bigger than 1. And then the force of BC is P divided by tangent theta. Now at the end of the day, we might not know what this is, but let's do a couple. At 30, at tangent of 30 is the same thing as sine 30 divided by cosine 30. Well, I know that sine 30 divided by cosine 30, I know that's 0.5 divided by 0.866. So cool. I'm taking a small number, dividing it by a bigger number, so I must get a smaller number. Well, let's say 0.4. But now I'm putting 0.4 in here, so I'm still taking my initial design and dividing it by 0.4. So hey, we get a larger number, and we're going to get a number bigger than 2. Oh shoot, that's not right. Let's say sine 30 divided by cosine 30. Where am I going wrong? Oh yeah, this is. I'm sorry. It is a number less than 1. But this number is bigger than half, so this is 0.557. This one's a little bit tricky, because now we're going to go P divided by 0.57. If we did P, we're still dividing by a number less than 1. So P is going to be a multiple of 1 time, it's like 1 point something. But because if it was P divided by 0.5, that would be 2P. But if this number is slightly bigger than 0.5, we're going to have a number that's less than 2. So that's where we get this 1.73, and you can just do that with your calculator. 1 divided by tangent 30 is 1.73. Cool. And at 30 degrees, we said, hey, this force is going to be 1 divided by sine 30. This is 2. So the force in member AC is going to be 2. The force in member BC is going to be 1.73. So again, the force in member BC is less. That's all we're trying to get, is just a relationship between we're going to try to find the force in AC and see if the force in BC is less. So we did it for there and check. And we do it for 45, and this number is bigger, this number is smaller. Bigger, smaller. Bigger, smaller. You know what I mean? So how about the extremes? So sine of 90 is 1, so P divided by 1 is 1. Okay, but how about the tangent? Tangent is sine of 90 divided by cosine 90. So sine of 90 is 1. Cosine 90 is 0. 1 divided by 0 is infinity. But now I got to throw infinity right into there. So now I have 1 divided by infinity, and that's 0. 1 divided by a huge number is 0. So yeah, there you go. 1 divided by tangent 90 is 0. And then, and both these are infinite. You know what I mean? Sine of 0 is 0, but it's on the bottom, so 1 divided by 0 is infinity. Same thing with this. Tangent is the same thing as sine 0 divided by cosine 0. So that's just tangent, and we know that that's 0 divided by 1. So this is going to be 0, but then throw it into here. Now we have 1 divided by 0, which is infinity. And but at the end of the day, what we're seeing is that the force in member AC is always larger than the force in member BC, no matter what. This problem would be cool if at some weird angle the force increased in member BC. Like, so even like right now, I could do a 3-star problem by coming up with some sort of geometry that when the angle goes from 0 to 90, there's some point where this member BC takes more force than member AC, because then your sweet spot would change. You know what I mean? So that would be a 3-star problem. All right, so what we're going to do is throw those two equations into our calculator. This is P sine theta, and this is P divided by tangent theta. So now, and that's the whole deal. You know, spend 3 hours on a problem, and you can really just now spit out the correlations. You're spitting out the ratios. Anytime you're using sine and cosine, again, now you're just using ratios. Think of it as ratios. Think of it as percentages. Heck yeah. All right, let's throw these into our calculator. So we have 1 divided by sine x, and then we're going to go 1 divided by tangent x. And our numbers are 2 and 3. We just want the positive. So that if you're real smart about this, you can go, hey, my x is going to be 0, my max is going to be 90, and my y is going to be 0 as a min, and my max, hey, the biggest number is 2, so let's go to 3. Okay, now I'm going to graph that. And now I get, well, and these are going up, these are infinity. So, you know, only at 30 degrees does this 2 pop up. You know, so 30 degrees is right there. But at the end of the day, what this shows, and I'm going to trace these, it says that this tangent one is always less. See how that tangent line is always under the 1 over sine. So this proves, and we'll actually get a y max of, how about 50? There you go. So now you see that goes to infinity, and that's not very good, but how about 20? Because we still want to see that red line is always under the blue line. I mean, that's all we're going for. That's all we're demonstrating. Is that, I mean, we're just really, you know, probably wasting too much time on this concept, but this is a check on reality that, hey, the force in BC is always going to be the force in this member always less than the force in this member. Now this member is in compression and this member is in tension. So another way to make this problem 3-star is have the stress, the compressive stress, you know, the compressive stress would be, you know, the axial or normal compressive stress. Have that number be less than the allowable stress and tension. So the allowable stress and compression, just have that be the allowable stress. I don't know. I don't know if that would generate a tipping point where it would change the angle. You know, that could also be another 3-star problem. But I'll look into it. Try to make my own problem. All right, so we're done with that. I'm going to erase those graphs, because now we're going to throw some more time on the clock. But now we and we're going to use this relationship to be like, oh, okay, once we figure out the force in A, then we can go buy steel at the steel yard because we found the thickness. Once we found the thickness in A, it's the same thickness in B, so we can just find the weight in both. All right, heck yeah. So now we go back to this equation where the weight is related to the, and we can even go back to this one. The weight is length times the area of C, weight density, plus the length of BC, area of BC times weight density. And the only thing, the area is what we're sizing based on the allowable stress. So if you can see that in the equation is force over area. So area is equal to force over allowable stress. We're going to say unit width of B. So at the end of the day, we got thickness is equal to force over B allowable stress. That is the equation for that. And then the force is going to be force in AC, because that's going to be the max force that we're going to design for. And we know that, so that's your thickness. And how to make this thickness as a function of theta. We'll throw in the equation for the force of AC. We've done this enough that it's P over sine theta. And now we're going to divide by B sigma. So this is fully fleshed out. I even put the B in there because we don't want to lose. We want to make sure this is in pounds. This is, B is in inches. Stress is in pounds per inch squared. And so one of these inches cancel. The pounds cancel. Inches goes to the top. And we get thickness in units of inches. Cool. And this is going to be the thickness of AC as a function of theta. Once we get the thickness of AC, we can find the weight of AC, because well, let's redo the weight equation. Weight is going to be length of AC times the thickness of AC as a function of theta. Length of AC is a function of theta. So now we're really doing the math, you know what I mean? So now we can come in and be like, oh, this is what mathematicians do. They're like, yeah, length is a function of theta, thickness is a function of theta. And I know what that equation is. Here is thickness as a function of theta. And then we don't need to multiply it by the unit width, because we're going to do that's constant, and that's constant. Now we're going to add it to the length of BC. We know, right now I can just say, hey, the thickness of BC is the same thickness of AC as a function of theta, because we bought the same material at the steel yard. That was part of the problem. Hey, go buy the same material at the steel yard. Cool. And now again B, and then unit density. Cool. So now we're just, we can factor out the constants. So now we're going to get weight is B unit density parentheses LAC function of theta, and even right here I can also, I should have done it in 2 steps. Yeah, let's do it in 2 steps. So we're just going to factor out those two like I said, and then we're going to get LAC function of theta, thickness AC function of theta, plus length BC. That's a function of theta. No, this is a constant too. Length BC is just 1. That's not even a function of theta. And then thickness AC is a function of theta. Cool. So now what we can do is factor out a TC. Cool. And we can just say length of BC. Well, we can leave it in there. You know what I mean? But we want to just call it 1. But no, what we want to do is get that golden equation where we can throw in the length of BC, where we can throw in the design load, where we can throw in the breaking stress of the material, because maybe we're not using steel. The allowable tensile stress. And we're going to throw in the weight density of the material. It might not be steel, but these are all constants that we know based on the orientation of this object. And okay, so what were we going to do? Weight, we're gonna have these constants outside, but we're going to factor, we got 2 of these. Thickness of AC as a function of theta, because the thickness of both members were the same. That's where that comes from. So we have B, weight density, thickness of AC as a function of theta, and then we have in parentheses length AC as a function of theta plus length BC, which is just a constant. So I'm going to underline the constants. There you go. So everything else is a function of theta. Now we're going to grab a fresh sheet of paper and kind of write that at the top, because this is our gold equation. You know what I mean? If we were mathematicians, we could just go right to this, but we're engineers, so we just have to play around a little bit. Okay, hell yeah, hell yeah. Ugh. All right, so now we just throw in the equation. So what the hell did we say TAC was? Well, yeah, we're not going to rederive it, but we already did it. TAC as a function of theta is P over sine theta, B stress allowable. Cool. And any other things? LAC. Yeah, LAC. Just from observation, we know what LBC is. Well, yeah, so that's what you would need to know. You would be let's see if we can do this in one swoop. LAC is what we know. LBC, that goes on top because we're going to divide by a smaller number. BC is the if we're using this angle, this is the adjacent. This is the cosine component. So we're going to go cosine theta. So there you go. So these are your 2 equations that you would pop in to here. So let's do it. So we have the weight is B, weight density, times P divided by sine theta, B, strength of steel. Hopefully I just call this strength. I have a hard time calling it normal stress. I have a hard time calling it anything but strength. Cool. And then parentheses. So we have this LBC over cosine theta plus LBC. Cool. So here's our equation that we could put into our calculator. We could say, hey, maybe I want this B to be a different width. This is the width B. And then here's the angle theta. P is the design load. Stress allowable is the material strength. I'm just going to call it strength. I think you get it's the normal. It's two things because, hey, I'm calling it strength because it might be the tensile strength in AC, but it also might be the compressive stress. But we are going to say this equation is only. Oh man, more light. All right, thanks for bearing with me. So this equation, though, is only if the tensile strength, I guess I'm going to say it, the tensile stress, the allowable tensile stress of the material is equal to the allowable compressive stress of the material. See, I just do not like the verbiage of material mechanics. I think I like my idea of just calling this strength and then kind of having an understanding of what it is. You know what I mean? It would be like if you had to call angle, instead of just calling it the angle, you had to say like, oh, it's the radial defecation of a circle. You know what I mean? It's just it's a word salad of it's awful. I do not like material mechanics from the verbiage perspective. Just call it strength. Just call it a friggin' angle. Call it a length. You know what I mean? If you had to call a length some sort of hypothetical, abstract, one-dimensional abstract of a three-dimensional object. You know what I mean? If you had to use those words every time you had to use the word length, no one would want to talk words at all. Okay, so this equation only works for this if you buy steel. Steel is the same tensile strength as it does compressive strength. See how I use the word strength there? Hell yeah. All right, heck yeah, home stretch. So when we put this into our calculator, you're going to get an equation like that. I don't want to do it yet because we're trying to tackle this as mathematicians. And if we do this, we're saying, hey, up here, if we change theta, if theta is 0 and we go to theta of 1 degree, which is a very small, change in theta is small. You know what I mean? We're just going to do a little small number. Hey, but guess what? We just went from infinity to like 55. You know what I mean? Like that. We went from infinity pounds to 55 pounds. Like the difference between infinity pounds and 55 pounds, it's a big difference. You know what I mean? So like even just right there, that is fundamentally explaining what differential calculus is. Differential calculus is, hey, I have this relationship that I'm saying as equation. I have weight over here, and the only other variable of concern is theta. So this equation, weight, is a function of theta alone. Everything else is a constant. You know what I mean? Is a property that I just choose one time at the beginning. Cool. So we have a function of theta that is some, you know what I mean? I'm not going to say constant, but yeah, some proportional constant stuff going on, and then you have the variable angle. So you have the angle, you throw in an angle, you pop out a weight. And so when we take the derivative of a function, so we have a derivative of a function of x dx. That's why math is so ridiculous, because you're just like, this I don't like it. It doesn't make sense. But if we say, hey, so we're just going to erase that right now, but keep that in mind. We're going to say, hey, if I change the angle, so I'm going to, and I changed the d into a caret. Change the angle. Change the function. You know what I mean? So hey, so that is the definition of a derivative. Derivative says, hey, if I change the angle by a little bit, how does the function change? And all this pops out is m, is the slope. You know what I mean? So hey, let's see if I can actually do some provational mathematics. So equation of a line is mx plus b. So right here, I'm going to change y. I'm going to change x by a small amount. I'm going to go from 0. So in this case, if I throw in x is 0, y is b. Cool. And then I'm going to throw in 1. So, and then I'm going to get y is m plus b. Cool. So then my change will be 0 to x is just 1. My change in x was just 1. So now my derivative is just change in y, which will be m plus b minus b. So then my change is m. Cool. So oh, that proves it. My change is the slope. Yeah, that's the whole deal. And all we're getting at is like, hey, I don't want infinity pounds. I don't want to make this infinity pounds with an angle of 0. I don't want to make this infinity pounds with an angle of 90. And I see that there's a sweet spot. There's a minimum number of pounds right there. And if I graphed it and just went to that location, I'd be like, hell yeah, 45 degrees. So that's a little foreshadow what we're getting. But I want to use, derivational... I want to use calculus, or, differential calculus, I guess is what you'd call it. I don't even know if that term makes sense. But yeah, we're going to use derivatives. We're going to take that function and find the slope. But we want to find the slope at all points. You know what I mean? So we want to get an equation. This is the equation of the line. What we want to do is get an equation of this slope. And essentially... the slope right here at this minimum, m is 0. The slope is 0. So when we get the equation, that's the hardest thing. And we're going to spend some time on this because we have to understand what we're going to learn is what's the derivative of sine x dx. And then what's the derivative of cosine x dx. I want to learn this. I already kind of have an understanding, but it's still I have to scratch my head. Even my brother, who's a mathlete, still has to go back. We talk about going back to this, and the more you go back to this, the faster it'll be. You know what I mean? Because what's the derivative of sine x? If you just memorized it, that is the dumbest thing. You know what I mean? Forget that you ever memorized it. You might as well just look it up in a book every time. There's no reason to memorize it because you can memorize it wrong. So we're going to figure out the fundamentals of what the derivative of those two are. But in essence, we have an equation for this line, and we want to find where the slope is 0. So the whole idea of derivatives is, hey, let's get another equation called the derivative of the weight of theta with respect to theta, and just put that aside for a second. But what that gives you is an equation. You know what I mean? So some sort of k prime. Of theta, you know what I mean? And in our case, it'll be like k prime theta plus, k double prime theta plus 1 and a parentheses, you know what I mean? But anyway, it is going to pop out for every theta. This is going to give you the slope of this equation. And so when this equation is 0, so there's some theta where this equation is 0. So we're going to go 0 to 90, and if we found the derivative of this equation at 45, well, let's just do it here. Right here, we have infinity, and then let's do it. The derivative of this is we're going to change the equation. Change the equation by the change in the angle. So we changed the angle. We went from 1 minus 0. That's the angle. So we went from 0 to 1, but the caret theta is saying, hey, the second part minus the first part. So 1 minus 0. Same thing here. This is going to be 55 minus infinity. Well, perfect. So now 1 minus 0 is 1. 55 minus infinity is like basically negative, pretty close to infinity. So the slope of this line is negative infinity. So at 0, we're going to get negative infinity. So I kind of drew this wrong, but at 0 we're going to get negative infinity and we're going to pop up. So here's the equation for this. So we're going to pop up. And then over here at 90, how about we go to 89 degrees to 90? So the change in theta is 90 minus 89, which is just 1 degree. And then the change in the equation is going to be infinity, the second part, minus 55. Cool. So we get positive infinity. So at 90, the slope is positive infinity. So now we're going this way. So now let's choose. Even for our problem, can we choose? Well, this is where you would need to do Excel, and I'm not going to take this problem to Excel. But let's say you wanted to find the slope of this line. So this is 0, 90, 45, at 30. Like right there, what's the slope of it? And just visually, hey, look at this. The slope of the line looks like -1. You know what I mean? At some point over here, you get a slope of +1. Like the slope of this line is this direction. This equation of this line is 1. The equation of this line is -1. You know what I mean? So the slope of it is -1. How would you find that? How I would do it is I would say, hey, I'm going to solve the equation at 31 degrees. Cool. And then I'm going to subtract that by solving the equation at 30 degrees. And then I'm going to say my change in the angle is 31 degrees minus 30 degrees. So this just becomes 1. And literally, the equation at 31 minus the equation at 30, and if we take the equation at 30, we're going to get a bigger number than the equation at 31. But that change, this change might be pretty close to 1. That's what this says. And at some point in here, there'll be a change in 1. And then so the slope will be. All right, hell yeah. I'm glad my battery overheated, because we can take a pause on this, because we have two different things going on. But this equation is going to give us the weight at 31, and this equation is going to give us the weight at 30. And this is the change in angle. So the change in angle is 1, but I said, hey, there's a point where the slope can be 1, and it's negative. It's going to be -1. But there's a slope, that can be, 1. And so what that means is that maybe the weight at 31 is 6 pounds. 6 pounds. And the weight at 30 is higher up on here, so that's going to be 7 pounds. So we would have 6 minus 7 pounds. That would be -1 pound and change. A change of -1 pound over a change of 1 degree. So that slope is -1 pound per degree. So now we're even getting units on it. You know what I mean? Because once we get that equation for that line at that point, what's that going to tell us? It's going to say, hey, we're going to have a change of -1 pounds per a change of 1 degree. Cool. And your change in degrees is always the same. It's you're gonna change your degree by a positive number, and then you're gonna see what happens with that. So if we went back to 0, change between so we would go 1 minus 0 degrees. Our change would be, hey, 55 pounds minus infinity pounds, and obviously you would get a change of pretty close to negative infinity pounds, and over a degree of 1. So our slope is going to be negative infinity, which what we see here. So there you go. The slope of this line, the slope of this line is negative infinity. When we graph the derivative of this equation, it's just going to pop out negative infinity. So if we go to 0 or 1 degree, we go all the way down to a point at negative infinity. Cool. I kind of want to do this for this equation, though. You know what I mean? So could we... Well, let's get the unit. You know what I mean? If all these are constants, we can also just get that quick and easy that says, hey, weight 1, 1, 1, 1, 1, length is 1. Cool. So we're just back to 1 over sine theta parentheses length of BC. That's 1 over cosine theta plus 1. Okay, and now let's evaluate it at, now we're going to do this, we're going to do the derivative of this equation and with respect to the change in theta, and we're going to take theta at 30 degrees and theta at 45. So our change in theta is going to be 45 minus 30. Cool. So we're gonna have to divide by 15. You know what I mean? So it's not a divide by 1 scenario. So whatever number we get, we're going to have to divide by 15, and then that is our slope. Cool. So let's throw in 30. And see if we can do this just, you know, with mental math. Sine of 30 is 0.5. 1 divided by 0.5 is 2, so we'd have 2 there. Cosine of 30, same thing as sine of 60, which is 0.866, so we have 1 divided by 0.866. That's going to give us a number greater than 1 plus 1. So we're going to get like 2.2. You know what I mean? So let's just guess this out, and we're going to get 2.2 times 2. That'd be 4.2. All right, so at 45, sine of 45 is 0.707. You should know the inverse of 0.707, or just that 0.707 is square root of 2 divided by 2. Did I get that right? Yeah, it is two, so the inverse of 0.707 is the square root of 2 over 2. Yeah. Which is 0.707 is 1.414 divided by 2. So what's 1 divided by 0.707? Well, check this out. If 0.707 is the 1.414 divided by 2, cool. What's the inverse of that? That's going to be 2 divided by 1.414, which is 1 divided by 0.707. Cool. So I just proved that inverse of 0.707 is 1.4. Is that right? Holy, I feel like I'm losing my brain right now. Sine of 45. Inverse that, yeah, 0.141. It just seemed kind of weird to me. Okay, so for that value we get 1.41, and then this is going to be 1 divided by cosine again. It's 1.41 plus 1. So we get 2.4 times 1.4. So 2.4 times 1.4 is 3.36. So cool. We get a change. So that's going to be at 45. So we'd get 3.36 minus 4.2. How about 3.4 minus 4.2? So we're going to get kind of like a negative 1. A negative 1 divided by 15. Even there, we're at a pretty shallow angle. You know what I mean? So there you go. I got to throw some more time on the clock. All right, heck yeah. But let's do this one for real. So obviously sine of 30 is 2, and then we're going to go 1 divided by cosine 30 plus 1 times 2. We're going to store that as x. So there you go. So we have 4.309 for at 30 degrees. And then at 45, we're going to get 1 divided by cosine 45 plus 1 times 1 divided by sine 45. Cool. That's going to be 7.65. I'm going to store that as alpha b, x is stored as alpha a. So we're going to go b minus a, or the 45 the equation at 45, which was 7.6 minus that 4.3. So we get a change of 3.34 pounds, or unit pounds, for a thing that we're kind of coming up with. But yeah, we get a weight change of 3.34, and that's over a 15 degrees. So over 15 degrees, we're reducing the weight. And that's kind of what we're seeing. We're just like, heck yeah, we want to reduce the weight. And so at 30, we're going to be 3.34 pounds heavier than at 45. So we divide by 15, and we get a slope. We get a negative slope of negative 0.2. There you go, 2 pounds per degree. Per 1 degree, we get a slope of negative 0.2 pounds. So there you go. So it actually, to get a slope of 1, that might be like at 10 degrees. So let's try that. Let's try 10 degrees and 11 degrees. And we'll just throw it in. You know, just doing some of these, even not like, because I could take this to Excel and play around with it, but even just playing around with it on your calculator, it takes a little while, but it just gives you such an intuitive ability to learn derivatives. So again, we're going to try that, like 10 degrees right there, 10 and 11. So 10 is going to be higher, 11 is going to be lower. We're going to go 1 divided by sine 10 times 1 divided by cosine 10 plus 1. Store that as alpha A, and then we're going to go 1 divided by sine 11 times 1 divided by cosine 11 plus 1. Store that as alpha B. Alpha B minus alpha A divided by 1. There you go. So, you know, even just right there, intuitively, I was just like, hey, can I find the point where the slope is 1? And I did. It's right. It's about theta is equal 10 degrees. The slope is, well, negative 1. So there you go. So at 80 degrees, I mean, can I confirm that? Is it a symmetrical thing? Probably not. You know what I mean? That's what we were thinking. We were thinking this is not a symmetrical curve. So let's do 80 and 81. And I'm just going to do 1 divided by... And the other way to do it is just go, hey, 80 stored as x, and then do 1 divided by sine x. Get your parentheses, a lot of parentheses. Just make sure you got enough parentheses, just so things don't get out of control. There you go. So I'm going to store that as our value for 80, and then I'm going to go 81 stored as x, and then I'm going to bring up that equation again, and then store that as alpha b. I'm going to go alpha b minus alpha a, and there you go. So over here at 80 degrees, I only have a slope of 0.6. You know what I mean? So my slope is shallower. So let's go to 86 and 87. So 86 stored as x. No. Let's go to 95. 95 stored as x, or just 90. 90 stored as x. Bring up that equation. Whoa. Yeah. No, not 90. I like 85. 85 was what I was thinking. 85 stored as x. And then bring up that equation. Store that as alpha A, and then 86 stored as x, bring up that equation, and then store that as alpha B. Alpha B minus alpha A is 2.85. Okay, so yeah, somewhere between 80 and 85, so about 83. So the graph is pretty similar, but it is just a little bit misshapen. All right, hell yeah. So now we have a thorough understanding of what derivatives are from a calculation perspective. I don't know why, it's a college 400 level class to really dive into, even just doing that, like picking a couple values and, that's not a college level thing, but analyzing those concepts, because that's how you program calculators. You're just like, well, what are we doing? We're taking a little value here, and then, hey, we get a number here. And then you're kind of doing if-then statements and be like, well, let's go to the middle. But anyway, so at the end of the day, the next thing we're going to do is we're going to take this equation that we came up with and take the derivative of it. So we're going to have to take the derivatives of sines and cosines. All right, and let's print out some more of these sheets of paper. Alright, heck yeah. So now we have the two equations written. Now we're going to figure out what the derivatives of sines and cosines are. Because deeply embedded in these equations are sines and cosines. So just like you might have an equation of y is equal to, you know what I mean, x squared plus x minus 1. You know what I mean? If you took the derivative, dy dx, and now anytime that I see dy dx, I'm smart. You know what I mean? I know that this just looks nonsensical. So I just say change in y, change in x. And even just today, just saying, hey, change in the equation, and then change in x. And that makes more sense because this equation, you know, even just right here, it should be an equation with respect to x. You know what I mean? So, I mean, essentially, this is where you get the function with respect to x. So then you have a function of x, and then you have f prime of x, which is the derivative of the function of x with respect to x. So then you throw the equation in, you know, x squared plus x minus 1, you know, derivative of this equation with respect to x. And that's where you get like, hey, change the equation, change x. So then this will give you one value. It only gives you one value. If you actually, you know, how integral calculus and differential calculus was invented, you know, then you do all the rules to be like, hey, let's derive this. Well, that's just 2x plus 1. You know what I mean? Like, why, though? You know what I mean? It's because of patterns and blah, blah, blah. You draw squares or however you do it. Slices, squares, you know, read all the little books that make 1 million views or whatever, make $1 million. But at the end of the day, it's just like, this is so much better of being like, oh, change the equation. So find the value of the equation, you know, equation at 2 minus the equation at 1 is your x at 2 minus x at 1. Now even this, I've never liked the way this was written, because even written it seems nonsensical, but just spoken, it's like, hell yeah, you know, evaluate the equation. So we could, like right at the get-go, maybe at 0, do you think we could figure out kind of what the slope of this line is? So we're gonna evaluate this equation at 0 and 1. Well, let's do 1 first. So we're gonna get 1 squared plus 1 minus 1. That's gonna be 1. And then we're gonna evaluate it at 0. 0 plus 0 minus 1. So that'd be negative 1. Cool. So now we have changed the equation was 1 minus negative 1. So that's how the equation changed, because here was x equals 1, x equals 0. Maybe I shouldn't have done it that way. I should have done it the opposite way. But now our change will be 1 minus 0. So that's going to be 1, and our slope is going to be 2, because these add additive. Let's do that again. So x is 0. We're going to get y is negative 1. And then we're going to go to x to 1, and we're going to get y is 1 plus 1, 2 minus 1 is 1. Cool. And now we're going to take the change in y, change in x. Change in the equation will be like the second, so we're going to 1 minus, negative 1 divided by 1 minus 0. So there you get the same thing. I just wanted to double check that the slope was 2. And now, this isn't 100% accurate. You know, to make this really accurate, this is the whole game you play. You make your change in x real small. So we're going to go x is 0, y is negative 1. And then we're going to go x is 0.1. What's y? I don't even know. But that's 1 over, 0.1 is 1 over 10. So squared is going to be 1 over 100. Cool. So that's going to be 0.01 plus x is 0.1, so we got plus 0.1 minus 1. So we got 0.11 minus 1. You know what I mean? Well, if we have 0.11 and minus 1, if we have 0 minus 1, that's negative 1, and then we're going to add 0.11. So that's going to be negative 0.89. Cool. So now we get negative 0.89, and I'm just going to do that in my calculator just to make sure. 0.1 squared plus 0.1 minus 1 is negative 0.89. So now I can see what the change in the equation was. It's going to be negative 0.89 minus negative 1. So these are additive, and then we're going to go 1 minus 0. This is 1. So we have, this is going to generate a positive 0.11 over 1. So now our slope is actually 0.11. Okay, so now we have a better understanding of our slope. Now let's try it again. X is 0, y is negative 1. X is, we're just going to go for it. We're going to go 0.001. 1/1000th of a change in x. And what's y? Well, we're going to go 0.001 squared plus 0.001 minus 1. And now we get the number is negative 0.99899. We're going to add 1, and then we're going to go 1 minus 0. So we're going to go this number plus 1. Did I do that right? Yeah, because it's this number minus 1. Cool. And then divide by 1. So now we get 0.001. So we see a trend, and this is really approaching, it looks like it's approaching 0. Yeah, I don't think there's any end in sight for that. And I was thinking it'd be shifted a little bit, but I don't think so. But let's do it with the derivative. Well, what's the derivative? Well, it's 2x, 2x plus 1. And and if you put this equal to 0, you're going to get 2x is equal to, yeah, that's why I figure I did something wrong or something. 2x plus 1 is the derivative, and if you set the derivative or the slope equal to 0, you're going to get negative 1. X is negative 1/2. So at negative 1/2, you're going to get 0. But at x is equal to 0, you should get a little bit of slope. And I don't know why we're not getting a slope to pop out. Oh, holy Toledo! Yeah, my bad. That's why we do it and make mistakes. So yes, my change in x here was 1, but then my change in x here is not 1. My change in x here is 0.1, 0 to 0.1. So we got 0.1 divided by 0.1. Well, guess what? That's really close to a slope. So we said the slope here was 2. The slope here is like, well, let's do it. 0.11 divided by 0.1. The slope here is 1.1. Nice. And then we keep doing it. Change in here is 0.001 minus 0. So we have to take this number and divide it by 0.001. And this number is going to be, if I recall, 0.001001. Cool. So we're going to take that divided by 0.001, and we get a slope of 1.01. So cool. It looks like at 0, the slope is 1. And guess what? You throw in a 0 right there, and you get the slope of 1. You know what I mean? Because this equation is the equation of the slope. Cool. You know what I mean? Like, I think this was a perfect one to do, this x squared plus x minus 1, because it shows that we have, hey, we have a little nugget of x there and a little nugget of x there. This is like, hey, let's say this was, let's say we just said y, or let's say we said weight total is equal to theta squared plus theta minus 1. Same darn equation. You know what I mean? And then we would figure out where is the weight the lowest? Well, when x is negative 2, you know what I mean? That wouldn't make sense because we're dealing with three-dimensional objects. But the process is the same. Change the equation divided by change the angle. You know, just by a little bit. Find that equation, which is 2 theta plus 1, and then you can figure out. All right, I ran out of juice, but yeah. So we took the derivative of this, and let's try one that actually pops out a value that's in the positive direction. So we'd probably do x squared minus 2x, 2x. You know, well, let's just say that. Plus, and then we'll go minus 4. So the derivative of, and then we're going to say, hey, this is theta squared minus 2 theta minus 4. That's our equation for weight. So our dWt with respect to theta would be 2 theta minus 2. Cool. So we're going to, at theta is equal to 1, there you go. Theta, when you set this equal to 0, theta 2 minus 2, we're trying to find that slope where the weight is minimum, is equal to 0. Bring the 2 to the other side, and then theta, and then divide by 2. So theta is equal to 1. And let's say this is in radians, because 1 radian is 60 degrees. So this equation is perfect. At 60 degrees, our weight is going to be minimum. If this is an equation for the weight of the system, our weight's going to be minimum at 60 degrees. And what I'm getting at here is using, what is it called, differential calculus, or or just, yeah, I'm just going to say that. Using differential calculus, and what we learn in differential calculus, I mean, you have 3 terms here that you have to take the derivative of. If you're going to take the derivative of the equation, and you have pluses and minuses, you can take the derivative of each term. You know what I mean? So that's, hopefully I'm not totally botching that statement, but that's exactly what you do. Now, if you have like x, this will be cool, because this is just a way to prove stuff to me. And let's at least write this equation down, just so we get really familiar. Because sometimes with sines and cosines, you don't even want to write them. You don't even want to write the word sine and cosine. You're just like, I don't want to confuse my brain. But let's get back to it, because if we have an equation, just a y is equal to x times x squared plus 2x, and I want to find the derivative, dy dx. Again, this is the derivative of this equation, y with respect to x dx. Like, just writing it like that might make more sense. Or change in the equation of y with respect to x by changing x. So you see that we have an equation with x in it. Cool, that's what we have, and we're going to change x by a little bit. Or, I mean, we're going to change x, but we're going to have to divide by that. This is the fundamental principle of why derivatives work, because essentially you're finding the slope. So if we go back to the simplest one, a slope of a line, here's 0, here's 1, here's 1. We're going to say, hey, we just want to know the slope. That's actually what we're after. We're after, how would we find the slope? This is y is equal to x. How would we find the slope? Well, we would evaluate x is 0, y is 0. X is 1, y is 1. Okay, let's throw it into our change. Our slope is rise over run. And if you think about it, what this says, if you start with x right here, and then you go on the run change the x, well, hey, your y is definitely going to change. And if we did the equation 2x, you know what I mean? Your slope is rise over run. What we're doing is systematically just changing the run by like a very unit, like we're like changing it by 1. But hey, with the slope of y equals 2x, our equation went up 2. So our rise went up 2. We changed the run by 1. Our rise goes up 2. You know what I mean? So that's where the fundamental principle of differentiating an equation yields the slope. You know what I mean? And for whatever property the slope is, You know what I mean? That tells you. Like for our equation, when the slope is 0, that was a magical point. You know what I mean? So that's sometimes what you want to know. Is like, heck yeah. And even on the extremes, it's like, whoa, I can just change the angle a little bit, and my cost went way down because I'm not using an infinite amount of material to build this thing on both ends. Cool. All right, so, but what I'm getting at here, because we're going to have to use all the principles that we know for differentiating and what we know about differentiating sines and cosines to do this one. So this, we have x times x squared. Now we could just say this is x to the third plus 2x and differentiate y with respect to x. That's just going to be bring the 3 down and then reduce the power by 1 plus 2. So that's the answer right there. But if we use, so what we're going to do, like even this material mechanics book, it has, like in the back, it's very useful, you know, just, and this is the stuff, it's like, it's just nice to know that the books, you know, have these identities, because what we're going to do is like right here. This is one that I just don't do a lot of calculus, but I'm getting better at it. And obviously differential calculus is what we're doing. So if we're taking the derivative of a product, u times v, you know what I mean, two different things, we have to go u dv dx plus v du dx. So let's do that. So u is x, v is x squared. Cool. So now, hey, we have a, oh geez, sorry. Hopefully that's a dx. Let me check. I mean du. There you go. dv dx, du dx. This is v. Yeah. U's and v's look identical when I draw them. All right, so du dx. And then again, you're just like, oh, this is an equation. This is, you know, if you want to write it out, this is the equation u with respect to x. You know what I mean? There you go. It's a function that has x in it. This v is a function that has x in it. Cool. And it's x squared. So when I change the equation, when I change the vx divided by a change in dx, there you go. We get the slope of this. So we're basically just doing mini slopes. So all right. So du is just 1, and dv dx. Sorry, put in the dx is 2x. Cool. Because like even just writing the equation, it's like, you know, even just writing df of x dx is like a 400 level thing to write. You know what I mean? It's you know, it tells a story of yeah, more than you want to know. So anyway, but that's why we're fleshing out that story. Cool. All right. So now we have everything. We have one. You know, we have an equation with 4 unknowns. There you go. And we just figured out the unknowns. So we have x dv dx is 2x plus x squared is v, and then dux is just times 1. Cool, and let's do this. So we have 2x squared plus x squared. Now, holy Toledo, I feel like, oh, yeah, we're still missing a piece because that was just for this term. Remember how I said if you have pluses and minuses, like we're just focused on the derivative of this term, and then we'll go on to the derivative of this term. You know what I mean? Do you want to do that same process with this? So let's write our equation. D dx, a product of u and v, is equal to u dv dx plus v du dx. I'm going to say u is 2 and v is x. So du dx is 0. And then derivative of constant is 0. And then dv dx is 1. So let's throw it into our equation, and we get the derivative of 2x with respect to x is, all right, I had to get some more time on the clock. And so what we're doing is we're doing this derivative of just 2x using the product rule. I kind of find it fascinating and fun. And so here is the answer for the product of a derivative. And so we got u first, so we got 2. dv dx is just times 1. And then we got plus v, which is x. Holy Toledo, I feel like I'm doing something totally wrong. Because dv, so see, I got them wrong. So du dx is 0. dv dx, so there you go. So u is 2. dv dx is 1. Perfect. Now the second part, v is x. du dx is 0. So this term goes to 0, and we're just left with 2. So there you go. Using the product rule on 2x. That would be a viral math video, and hopefully I make it. I don't know. I just do long videos. You know what I mean? I'm not about the algorithm. I think my videos are just, if you just want to space out for 3 hours and listen to someone ramble on about math. And we're pretty consistent about saying factual things. I do mess up a ton of, like, I get better. I do watch some of my videos where I get better at where I'm making mistakes. Like, definitely with units. Like, I'd be like, hey, 600 millimeters. You know what I mean? And it's actually squared, and I just kept calling it 600 millimeters. You know what I mean? That I understand would frustrate a viewer. And then even, I went from 600 millimeters, and I did divided by 10 to the 6 to get, you know what I mean? And then I just said millimeters again, even though it was a meter squared. You know what I mean? It was a conversion to meters squared, and I just kept saying millimeters. You know what I mean? Stuff like that, absolute, even drives me nuts. So we get better. All right, so we're going to use this product rule because, hey, we have a product of sine and cosine right here. You know what I mean? So that's going to be the first thing that we're going to take a look at. All right, but hell yeah. So now I'm going to write this equation again, and then we're going to try to use the product rule. First, we need to figure out what we're going to have to derive sine and cosine, so that's going to be the next thing we're going to look at. So let's write this equation one more time. 1 over sine theta. And I might even have this equation written wrong. You know what I mean? Probably not. I think we're pretty good on it. But we'll double check in the end and see if we made any mistakes. So what we really need to do is, hey, what's the derivative of sine of an angle with respect? Sine, you know, you can either call it this, or you can say, hey, derivative of sine x dx. You know what I mean? And again, this is derivative of the function sine x dx. You know what I mean? So, and again, this is like saying, hey, we have a function of x that the function of x is sine x, and we want to take the derivative, f prime of x, which is the derivative of the function of x with respect to x. So there you go. And this is the change in sine x, change in x. So you can do it mechanically, but we want to do it, we want to figure out what's going on. So we're going to go 0 to 90, and we're going to go 0 to 1. Sine of 0, and the equation that we're chilling out is sine of theta, sine of x or whatever. So at 0 degrees, sine of x is 0. At 90, sine of x is 1. Cool. Now how do we get from here to there? Do we go this way? You know, how many different ways could you go? Could you go this way? You know, we know it's a kind of a curved path. We definitely know it's not straight. But now let's throw some values in. So definitely go 30, 60. I stay away from 45, but so at 30 degrees, sine of it's halfway. So there you go. So see how we have 30, 60, and 90? We have like you know, if you went on a straight line, like this sine of 30 would be a third, but it's not. You know what I mean? It's half. So even just right here, we know we got to get from there to there. And if you know anything about sine x, is sine of 30 is 0.5, and then I always write sine of 15 is 0.25. And then, this is just a good one to do. Sine of 7.5 is 0.125. Sine of, what's half of this? 3.525. You know what I mean? Is 0.0625. There you go. You know what I mean? And these are approximations. You know what I mean? Sine of 30 isn't, well, sine of 30 is 0.5, but but it's fairly linear. Sine of 7.5 is pretty close. Well, it's actually 0.13, but close enough. So what we know is that this relationship is fairly linear. You know what I mean? But it's kind of curved up just a little bit. So there you go. So it's linear from there to there. And then what? So even if you just do that and then draw a straight line, like, hey, that's a pretty good approximation of sine. So now let's go over here and do cosine. So we're going to do cosine theta. Here's 1, here's 0, here's 90. And then we're going to do three sections. We're going to do 30 and then 60. So cosine of 0 is 1. Perfect. There you go. Cosine of 90 is 0. So now how does this look? I mean, are we just going straight down? Probably not. Are we going like this? I don't know. Are we going like this? Those are kind of the 3 curved paths that you could probably take. So let's flesh it out. Do we know anything about cosine 30? And my MO is know your sines. You know what I mean? Start with sine 0, know that's 0. Then go sine 30, know that's 0.5. Then go sine 45, and know that's 0.707. I think 007 for this, just because there's maybe 2 sevens. There's not 2 zeros. That wouldn't make any sense to go 0.700. Or 007, obviously that wouldn't make any sense, or 007. But anyway, think 007, and then you can kind of figure out where they go. And then sine 60 is 0.866. I just remember this because it's close to 85, you know what I mean? And then, and why I know it's close to 85, because it's close to 100%, you know what I mean? At the end of the day, I know it's a reduction of 100, but it's closer to 100 than it is, like 0.75 or 3/4 of the way. Cool, and we might talk about that one in a sec too. And then sine of 90 is 1. It's because, this one, you can always, it's very good mentally to approximate that it's also 1. Because if you do that, if you say, hey, the sine of 90 is 1, but the sine of 60 is approximately 1, then you have this graph, you know what I mean? Which might make more sense, and it's actually kind of closer to what's maybe going on. So then when you go over to cosine, and the reason I just spent about 5 minutes saying memorize your sines is because then you can easily do the cosines. So cosine of 0, cosine of 30, cosine 45, cosine 60, and then cosine 90. Well, obviously cosine of 0 is 1, just because it's the opposite of sine. I think we can just for sure remember that sine of 0 is 0, and that cosine of 0 is the opposite. It starts at 1. So that means cosine 90 is 0. So now we have just a relationship that's like, whoa, it just feels kind of like backwards, and it is. So if we start at 0, cosine of 60 is going to be 0.5. And the equation for this is cosine 60 is the same thing as sine 90 minus 60. I don't think you should memorize this equation, but you should be able to be like, oh yeah, how do I get to it? Because I know cosine 60, isn't that just sine 30? You know what I mean? And isn't that the case? Isn't that what this equation says? Cosine 60 is sine 90 minus 60. Yeah, it's sine 30. So if I go to cosine 60, I can just know that sine 30 is 0.5 and type it in. That means cosine of 30 is sine of 90 minus 30, that's sine of 60, which is 0.866. So these two charts in 0.7 and 45 is always the same. So those are the two things, because I use these numbers all the time. More time on the clock. Alright, heck yeah. Okay, so back at it. So now we can flesh out what cosine is. So we're saying cosine of 30 is sine 90 minus 30. That's going to be the sine of 60, which I know is 0.866. So we go 5, 6, 7, 8, 9, 10. And yeah, so it's going to be all the way up here. There you go. And like I said, didn't we say that sine of 60 is close to 1? So we can even put it up there too. Cosine 60, that's going to be the sine of 30. That's going to be your 0.5. So here, now we have a nice relationship. It's just kind of the opposite of what we have here. So now you have something that looks linear here and then goes up. And, obviously, like, sine looks like this 90 and then up. And then it does the same thing this way. So there's sine. And then cosine kind of does the opposite. We're going to start up here and then go down. Yep. And I guess we're doing the opposite over there. I think I have that right. It doesn't look right, but no, it's just because you have 3 segments. If you ever remember this, you kind of have 3 segments here and kind of 2 segments there. So if you remember that, so if you do sine and you draw it out, you go 1, 2, 3, and then just 1, 2. So then at 30, you're halfway already. So then you go up here, and then you taper out. So there you go. And then you go 1, 2, 3 the other way, and then 1, 2. So now you're going down to here, and you're trying to get to this 1. So now you're tapering out. So there you go. There's your nice smooth sine. And I guess if you did the opposite on the same graph, you would start up here. Here's your halfway point. And so you're coming up. I mean, obviously 1, 2, 3, 1, 2. You would do the same. But yeah, that's why it just kind of looks interesting when it's only done. When the cosine's only drawn like that. And I might have something wrong here. I don't think so. I think we're good to go. But what I'm really wanting to show is now we want to know the derivative of sine of x dx. And even just saying that, it's just like it seems nonsensical, but we can go back to what's the derivative? Well, when we change x by a little bit. So if we take the value of sine at 0 and 1, how did the function change? Well, it went up. So sine of 0 is 0. Sine of 1 degree is, well, let's not do that. Let's do sine of 30 is 0.5. And, well, how do we get the slope of 1? You have to go to radians, and oh my god, like, do we want to explain radians? Sure. So radians just means the radius of a circle. That's where it comes from. And it says, hey, this is our circle, and we're going to go up 30 degrees. And what does this even mean? Remember, 30 degrees, this vertical component is going to be 0.5. Well, didn't we just say sine of 30 is 0.5? Booyah. And this is the unit. And this radius is a radius of 1. And so what radians is, so if you have an angle in radians, in 1 radian, so let's say I have an angle of 1 radian. What the hell does that even mean? So let's say you think this is just a bizarre label for an angle. All you have to do is take radians times radius. My MO is you have to take something that sounds nonsensical and multiply it by something that makes sense. You're taking radians times the radius, and this pops out something normal. So there you go. And the something normal in this case is this length. You know what I mean? This vertical length. So if we have a... Oh, no. Never mind. Let's pop back, because what is 1 radian? Like, no one knows what's 1 radian is, and it's approximately 60 degrees. I would just call it, it's like probably 57 or 50. I don't know what the hell is 1 radian. I don't even know how to type in 1 radian. Anyway, oh yeah. Well, there's a circle is holy hell. Why is a circle 2 pi? Oh yeah, it's 2 pi radians. So yeah, it is great. Yeah, if you have a radius of 1, and here's your circle, what's the circumference? You know what I mean? So that means the diameter is 2. That means the circumference is 2 times the diameter. It's 2 pi. Cool. So the circumference of a circle with a diameter of 2, which now that seems nonsensical. We always do this unit circle with a radius of 1, but it has a diameter of 2. You know what I mean? It kind of is confusing when you're just like, no, this circle has a diameter of 2, and the radius is 3 times that. It's 6, you know what I mean? So at the end of the day, 2 pi is synonymous with 6. That's the circumference. Okay, so now we have this thing called radians. It's because this. If we take this circle with the radius of 1, and then take this length and then make strings that have a unit of 1, and then start draping them over this circle, we'll get like 1 there, we'll get 1 there, 1 there, 1 there, 1 there, and 1 there. And we'll get a little extra, because 2 pi is 3.14 is 1 pi, so 2 pi is 6.28. See, you just multiply by 2. So you'll get 6 string lengths plus a third of a string length, a little extra. And that's the circumference of the circle measured with a radius, like made into a string and then draped around a circle. Cool. So how does that involve the angles? Well, if we have 2 pi radiuses, if we have 6.28 radiuses per a 360 degree circle, well, now we know we have a conversion between so we're saying when we drape, all right, hell yeah. So we're saying when we drape this radius along this circle, we're sweeping out an angle. So what the hell is that angle? Well, you use this equation that says, well, we could sweep out 6.28 radiuses of rope for 360 degrees. So what's just 1 radius? And it seems like maddening math, because you want an intuitive understanding of it, like at every little point. But let's see if we can get there. 6.28 radiuses, I'm just going to say radiuses per 360 degrees. So I want to know what 1 radius is. So I actually have to flip this over, yeah, I just think I have to invert it. You know what I mean? So we would have 360 degrees divided by 6.28 radiuses. This literally, by dividing this number and getting a non-fractional number, 360, we get 57.32. I mean, it's a non-fractional number, but you can put it over 1. So there you go. We get 360 degrees per 1 radius. So there you go. That's how they get this. 1 radian, and they call it just radian. This is the definition of what a radian is. if you had a radius and turned it into a string and then started draping it around the circle, you'd get to that point and it would be 57.32. Now, you can totally forget all that and just say, whoa, hey, what I have an angle with a radius of 1. Hey, I'm just going to know it's 60. But what the hell does that mean? It means that when I take a radius, when I take an angle with 1 radian and I multiply it by the radius, so I'm gonna radians times radius. Oh, that's right. Radians times radius is the arc length. You know, it's just a good equation to know, but that's where you get, you know, the correlation between radians and radiuses. That's a definition in itself. We took the radius and cut a string that was this long and then started draping it around the circle till we got this angle that we're calling 1 radian, and that's the equivalent to this arc length of 1 radius. So like I said, an angle of 1 radian times the radius gives you something normal, and that something normal is the arc length. Now actually, I don't even think that really helps us for anything that we're doing, but it was just an understanding of what a radian is, because now we know that a radian is pretty close to 57 degrees. I'm just going to call it 60 degrees. So what's a half a radian? If now you mentally know that a radian is 60 degrees, because if you draped a radius of string around a circle, you'd get to about there. Now the question is, what's half that? Well, it's 30 degrees. So a half, 0.5 radians, is 30 degrees. 0.25 radians is 15 degrees. You know, because sine it has a linear relationship from 30 to 0 that's almost perfect, and this linear relationship can be extended up to 60. It's still fairly accurate. That's why I put that value. That's why I'm saying sine of 60. You can just set it as 1, because you're saying, hey, a radian of 1 yields Now I'm confused. Yeah. A radian of 1 is synonymous with 60 degrees. You know what I mean? So there you go. That would be a okay. So what we're doing here is we're trying to find the derivative, and we're trying to find why this slope is 1. So without using any other paper, let's do it. Let's do it for this. So we're going to calculate in radians sine of point. So instead of 30, this is going to be 0.5. 60 is 1. 90 is 1.5. And does that make sense? Because pi divided by 2. This is 3.14 divided by 2. That's so close to 1.5. It's like 1.57. Who cares? It's 1.5. That's why we did these 3, hashes. So there's a lot of visual ways to understand radians. So now we're going to do degrees and radians. Sine of 0.5 radians is 0.5. Cool. Sine of 0 radians is 0. So when we take the derivative of sine theta with respect to theta in radians, we get, so let's write this out, theta is equal to 0 radians. That means sine of 0 is 0. When theta is equal to 0.5 radians, no, that's 30 degrees, sine of 0.5 is equal to 0.5. So now, the change in sine is going to be, the change in the equation is 0.5 minus 0 divided by, hey, how much did we change our angle? Well, we went from 0 to 0.5 radians, so that's going to be 0.5 minus 0. So now you see 0.5 divided by 0.5 gives us that slope of 1. Holy hell. That was a long way to get there, but we did it. So now you had to change it to, because the second you go to, if we keep in degrees and you do sine of theta, well, your window has to go from x from 0 to 90. And then your y just goes from 0 to 1. So your slope is hella not 1. You know what I mean? Let's graph this out. Whoa. That's not to scale. This is 90 and this is 1. So if we go zoom 6, look at that. You can't even see the slope. You know what I mean? Now we'll go window and we'll just go back to negative 1. Y is 0 to negative 1. Graph, bummer. Y to 1, there we go. So yeah, you'll see the slope is not 1 because degrees, you have to have 90 degrees, you know, so there you go. But in radians, yeah, you get this cool relationship that it's slope. Now it's only because someone chose to invent radians. You could easily say diameters. You could easily cut a string to the diameter of a circle and start draping that string around the circle. And guess what? You'd be able to drape that string around 3 times. You know what I mean? 3.14 times. And you'd have a 0.14 string of extra. So that actually really solidifies, you know, what the hell a radian is, because you could easily be talking about angles and diameters. You know what I mean? There's no term for that. That's why radians should be called just radiuses. The angle of radius. You know, but we use the term radians, and it's just the most. You have to go through this whole tutorial in your head to really flesh out what a radian is. It's worse than metric units if you're an English engineer. Holy hell. Okay. Or an American, I should say American. English, they use the metric system. Over in England. Alright, hell yeah. So now we have figured out what the derivative of sine theta right at the beginning is 1. Now, if we do it at the very end, you know what I mean, we're going to, we're going to change the radian by 0.5. So our change in radians is 0.5, but our change in angle is going to be real small. It's just going to be 1 minus 0.866. You know, if we did, if we did 60 degrees to 90 degrees, change in radians is 0.5. 1 minus 0.866 divided by 0.5. You know, our slope right here from 60 to 90 is a slope of 1/4. And as we approach 90, the slope goes to 0. So there you go. And so now, what equation makes that make sense? You know what I mean? What equation... Alright, hell yeah. So what equation, when we throw x is equal to 0 degrees or x is equal to 0 radians, is going to shell out the number for the slope, which is 1? What equation, when you put in 0, is going to be 1? Well, I don't know. Maybe your equation is x plus 1. You know what I mean? Hey, that's a pretty good indication of if you throw in 0, you get 1. But if you throw in a radian of 0.5 or of 1.5, hey, you get a steeper slope. You know what I mean? So no, our slope's got to go to 0. So at the end of the day, and you should just have in your back of your mind, hey, the derivative of sine is kind of like cosine. I just don't know if it has a minus or a plus. Because the derivative of cosine is sine. I just don't know if it has a minus or a plus. So this whole going through this whole show was just to really flesh out, hey, can we intuitively see, if I say sine x, or if I say sine theta, can I visualize this graph in my head and know that it starts with a slope of 1? So the derivative of sine x which says, hey, I want to know the slope at every point. And when I put in whatever equation that is, when I say x is 0, it's going to pop out y is 1. That equation is cosine. So derivative of sine, and I'm just even solidifying this in my head. Derivative of sine, I want 1 to pop out when I throw in x is 0. That's literally cosine. So the derivative of sine is cosine. Let's check it. So when I throw in 0, I'm going to get 1. Perfect. When I throw in 90, over here, I'm going to get 0. That's going to be the slope. So perfect. Now, let's find out why the derivative of cosine x dx now must be negative sine x. I think we've all run into this where it's just like, well, which one's negative? You know what I mean? So I'm going to say I have this graph. I have the graph of cosine, and its slope right at the beginning is 0. Okay. So that's one piece of information. But for this one, we need to know 2 pieces of information. So great. If this is the graph of cosine x, and I want to know the derivative of it, whatever the d cosine x is, that equation, when I plug in x is equal to 0, it's got to pop out y is equal to 1. No. Sorry. When I take the derivative of cosine x, and I plug in x is equal to 0, the slope is 0. So when I plug into that equation, I have to get 0. So the only equation that plugs, so if I do sine of x, hey, I put in 0 in here, I pop out 0. So isn't the derivative of cosine x 0? It seems like it'll work, but guess what? Look at how this cosine x drops. It goes cosine x, the equation, starts at 1 and then goes to 0. So you already know it has like a downward slope. The slope of cosine x between 0 and 90 is negative. So that's all you have to know, and that is the reason why derivative of cosine x is negative sine x. Perfect. So now we can move on from all that. We're going to grab a fresh sheet of paper. Maybe let my camera cool down. And what we're going to do is we're going to use those 2 things. Understand that we have a product here. And, I don't know if we have to get too complicated with our equations. We'll see. But hell yeah. Then we're going to figure out what our derivative is. Okay, catch you on the flip side. Alright, hell yeah, back at it. And, you know what I mean, so now we kind of understand how to derive sines and cosines, or take the derivative of sines and cosines, and we know the product rule, because we did that with a ridiculous 2x. We did the differentiating, I don't know if it's, yeah, I'm sure it's called the product rule of differentiation. I have no idea, but we did it for 2x, and so we're solid on that. But this equation right here yields this, and that is absolutely not what. Oh no, never mind. No, we're good. I thought I did this wrong, and I thought this equation was the one that should be like that. But well, yeah, no, duh. This is the one that should be like that. So no, we do have an error here, and I need to get a pen that works. Okay, so this equation was supposed to be for weight, and if weight was 0. Or maybe, let's zoom out to 90. So we're going to window and go to 90. Maybe it does go back the other way. We'll see. Yeah, I guess so. Man. Okay, yeah, so let's throw in our values just to make sure this equation is right. Because once we flesh it out, yeah, remember we said the unit length of 1 made no sense? You know what I mean? So we definitely have to use the equation that makes sense. So here we go. Weight with respect to theta is going to be that aesthetic thickness, I'm going to call B. That's kind of the width there. Weight density of the material. The strength, the design load, divided by sine theta, Whoa, do we have B twice? Man. Hopefully I didn't write this down wrong. But no, interesting. Yeah, we definitely have B twice. So yeah, that's fascinating. Yep. So we have this. Anyway, it doesn't really matter. B is 1 anyway. You know, for our design, B is 1. So those cancel, but who cares? And now we have length of BC divided by cosine of the angle plus length of BC. All right, so let's figure out, you know, do we want to make this 10 inches or 16? Let's make it, you know, like a normal shelf that's going to hold a lot of weight. And so we'll make this, or should we just do 10 inches? You know what I mean? I'm chill with 10 inches, so let's start there. So we're going to do W, so we'll put them in. So we got 1, weight density of steel is 0.29 pounds per inches cubed. This is, shoot, 1 inch. Okay, and then we have design load. We're going to put that 5,800 pounds on. That made sense. And then sine of the angle. The angle is what we're going to vary. So here's another 1 inch. Those cancel. And then we have the strength of steel, which is 58,000 pounds per inches squared. So obviously these 58 hundreds cancel. And now our length is 10 divided by cosine of the angle plus 10. So let's see if this gives us a more reasonable graph. So we got 0.29, 58,000 divided by, I better get another parentheses at the beginning. Alright, divided by sine x times 1 times 58,000. Cool. Another parentheses, and then we got to put this in. So 10 divided by cosine x plus 10, parentheses. Now we're going to graph that. Ooh, it is still... Man, I don't know why it's not giving me the values that I thought it was going to give. Oh, Toledo. Alright, heck yeah. So we're back, and we changed our graph. It was the same one. We just did like a zoom, you know, let's do a zoom normal, and then, you know, erase out, and then do a zoom fit. You know, it really wants to pop the entire thing in. And then it did that, and then so I went to 90. So x is going to be 90 degrees, and then graph that. So it really comes in and doesn't look like a parabola at all. It looks like it. It's because these are going into infinity. So as my y is just huge. So like, you know, if I'm saying this is only like 10 inches, this thing's only going to weigh 3 pounds, you know, this whole thing, like, you know, just obviously, if it's just like even 2 feet by 2 feet, how much is this metal going to weigh? No more than 50 pounds. So for my y max, let's go 50. And for my y min, 0, because it's not going to weigh negative weight. So then we're going to graph that, and then heck yeah. So this is 0 degrees all the way to 90. And you can still see it starts to go exponentially. So in between this point to 0, heck yeah, it goes all the way to infinity, and then between that point and that point goes to infinity. But heck yeah, so this is the generalization of our graph. I'm glad I typed it in right here, because this now gives us actual values. If we have 10 inches, and so let's go value at 30 degrees. Thing's going to weigh 12.4 pounds. Now we're going to go value at 45. It's going to weigh 9. So 12.4 pounds at 30, 9.9 pounds at 45. Let's go to value at 60, and it's going to weigh 10 pounds. And this really, because it's like oblong this way, this shows exactly what we were talking about, where it's just like, well, there could be, even though the lowest point is at 45, right at this weight of 9.5, you know what I mean, at a value of 60 degrees, the thing only weighs 10 pounds, where again the value at 45 weighs 9.9. You know, a tenth of a pound more in the cost of the steel, and I'm just going to maybe get definitely more hanging force. So, but this problem says, hey, they want to make sure that theta is decreased as much as possible. So I still feel like something is slightly wrong with these values going in, because it looks like obviously you should, 45, obviously you should make your angle steeper, because you're really not adding too much weight. But that's because this problem is designed to be like, hey, let's reduce the area as much as possible. Just to reduce the weight. What's the best weight reduction? The lowest point is at 45. Whatever the to accept the design load of P. But yeah. But anyway, because like I thought when we, well, let's maybe go back and do this one just a little bit, just to see what we have going on, because it's been a while since we came back to this equation. So we're going to do theta at least 30, 45, and 60, but 30 and 60. If theta, and we got a force of 58,000 pounds. Theta is 30. This vertical component is small, so the force in AC has to be double. Force in AC is going to be that 116 kilonewtons. Cool. At 60, and basically what we're doing is 58 divided by sine of the angle. So this one's going to be 67 kilonewtons. And then 58 divided by sine 45, we get 82 kilonewtons. Cool. And then, again, we've already said that the force in BC is irrelevant. It's always going to be lower. So we have to design, so this for steel is 58,000 pounds per square inch. Our equation is strength is force over area. So then our area is equal to force divided by the tensile strength allowable, which is 58,000. And our area, we're going to say area is B, and then whatever the thickness is. So we're trying to find the thickness, so we're going to say thickness B is force over allowable. We're going to get the B down here, though. So now this is their equation for thickness. So thickness for these angles is going to be this 116 divided by 58, basically that. So 116 divided by 58, thickness is 2 inches. 82 divided by 58, thickness is 1.4. 67 divided by 58, thickness is 1.15. Cool. Now, in these configurations, we have to figure out what the length is. So let's make this thing a lot larger. Let's go 24 inches on it just to make sure, and we'll go back in and change this length to 24. Let's do that in our calculator right now just so we don't forget. So everywhere there's 10, I'm going to change it to 24. Graph. And this is a smart thing to do. Anytime you get an equation, you're like, hey, that looks about right, but it just, for whatever reason, it's like, well, obviously I would make the angle a little bit more than 45. the question says, yeah, what's the lowest weight? It is 45, but I mean, be reasonable. Spend an extra $10 and you get way much more force. You know what I mean? Even though the halfway, the lowest point is right there. See, you almost take like the center of mass of the lowest point, like right around there looks like the best. The second it starts to tend up, this thing gets heavy and you're going to pay more money. But I would at least, I'm going to trace this out. Where I would put the weight, 24 pounds. So you know what I mean? So if this is 24 inches and this is whatever, I'm going to buy 24 pounds of steel at the steel yard. That's not much. I mean, steel at the steel yard, even if it's super fancy, for me it only costs $2 a pound because I get a deal. So hell yeah. So we're talking $50. So I either spend $50 and get more strength, or I go right to that 45 degrees and spend $48. You know what I mean? So for $2 more, I can probably get a lot more force. But I mean, the question is basically try to find where the slope is 0. You know, very mathematical, but kind of not practical. So that's why we're double checking, just to make sure we're doing everything right. All right, we're gonna put more time on the clock. All right, hell yeah. And sometimes it's a slow process to make sure you're walking back through everything just right. So this is going to be 24 inches now. The length of this is going to be, heck yeah, 24 divided by a fractional number to get a larger number. It's going to be cosine of the angle. So we got, so 24 divided by cosine of 30 is, so this is going to be length AC. Length AC, we're just going to do 27.7, good enough. 24 divided by cosine of 45, this length is 33.9. And again, 60, this length is 48. Okay, length of BC is just going to be 24. So now we're going to get total length. You know what I mean? It's just adding these up. So 27, so this is 51.7. 33.9 plus 24. This is 57.9, 48 plus 24. This is 72. So there you go. So yeah, it looks like it's significantly more weight at 60. So that's where I feel like my equation might be a little bit off, but we'll see. So now we found that out, and now we want to figure out what the actual weight is. Weight is going to be length total, or I guess we're doing, this should be length total. It's going to be length total times the area, which is just that BT, the thickness. And here's our equation for thickness. And if we go back, here's our equation for thickness. There you go. So we got our equation for thickness, which is a function of theta. B is just what we chose. Length total, you know what I mean? It is just, we're taking length B, BC, so that's not changing. But this length A is this. It's length BC, length AC is at 24 divided by cosine theta. So there you go. That is an equation. So this length total, let's write it up here. Length total will be length BC plus length BC cosine theta. I just have it kind of written opposite. And okay, hell yeah. And even right now, I can just throw in 60 and see what the weight is. So we're going to graph this out, and we're going to go trace value 60 degrees, and we get see, this is just popping out the total length. Yeah, so this equation that we made is just popping out the total length. That's weird. So we want the weight, and the weight is the length, 24 inches. No. That's weird. It's not even popping out. No. We're right because we're basically 72. The total length, 72 times 0.29. Oh. Oh, this is interesting, though. Okay, so this is what's happening. Here's our total length for this angle, and here's our thickness that we would need. So our thickness gets reduced. That's why this side of the equation is bulged, and it seems more better, is because when we do a longer length, hey, our thickness goes down. If we do kind of that 45-degree angle, sure, our length total's small, like relatively nice, but our thickness goes up a little bit. This is the best weight ratio. Okay, so our equation is good. So we got length total time, and then length times the area. Yeah, length times the area. This is volume. And then times the weight density of steel. And that's it. That would be the weight. The total length times the area. And yeah, perfect. So B and weight density is a constant. And then T theta is just going to be F divided by sigma B. But F, in terms of P, is going to be, so this is kind of the max, this is the force in AC. That is going to, that's how we got this, and it's going to be P divided by sine theta. Like right now I'm just going to get rid of these B's because we've obviously said they cancel. And now we're just left with the thickness. Or no, that was the thickness. So we have the length. Oh, so we were just starting with these two. B times thickness, that's all we've done. And the weight density, we've done all three. But now we need to multiply by the length total, which is, yeah, let's do it this way now. Which is the original length we chose, plus that length divided by cosine theta. Cool. So now this is constant, this is constant, this is constant, and we have two terms here. So let's bring our constants out to the front and put them in an order that makes sense. We're going to have P sigma phi, and then I kind of want to multiply this back in. So now we're going to have that length BC sine theta. Oh, and then length BC is a constant. So here we go. So we have P length BC. So yeah, PL sigma gamma, gamma, weight density. This is how you do it. You do the force, length, strength, and then gamma. And then you're bringing this sign. You're multiplying this sign into here. So we're going to have a sine of theta. So we're going to have a tangent, and then we're going to have a sine. So now we're going to have a sine theta plus tangent theta. Okay, so this is much different than I had last night. Last night I had a different thing going on. It kind of worked. I just wasn't able to double check it. So this, hopefully, I mean, yeah, that's what we got. And now we're going to differentiate. So now differentiating, and yeah, we don't even have to do a product. Well, last night I was thinking we had to do a product, but this still might be wrong. But the derivative of tangent, is secant squared u du dx. So if we have tangent of u, du dx is just 1 because, so there you go. So yeah, so now the derivative and sine. So remember, we have sine. It goes like this. Starts with a slope of 1. So derivative of that is just going to be cosine. And we can just double check. Always good to figure it out and then double check. So derivative of sine is cosine. Alright. So now you're going to have P, L, B, C, sigma, gamma, cosine theta plus secant squared theta. Okay, so now I'm gonna throw that into my calculator. And this will give the slope of the line. I'm just gonna plug that in. So cosine x plus, holy Toledo, I forget which one's secant. You know what I mean? Secant is to what is to whatever. Yeah, secant is 1 over cosine. So secant squared. Alright, I'm totally just writing this in, but it says in my book secant squared theta is equal to tangent theta squared plus 1. So there you go. So that's what we'll do. We'll do tangent x squared plus 1. Alright, now we'll graph that. And that should... See, yeah, no, yeah, we got something definitely wrong. Oh, this is a bummer. Alright, so I'm going to go back and write this equation and see if we can figure out a way to get a derivative on this. Alright, heck yeah. That's why we make these videos. I really don't like pausing. I like to talk through my errors, but that threw me for a loop. No. See how I had this sign, and then I multiplied it up top? That was so dumb. No. This is a 1 divided by sine theta, and if I multiply it through, this becomes sine theta, and this becomes sine theta. And then so from last night, this is a little bit, I got there kind of faster. I just didn't know exactly how to make the units match. You know what I mean? Here we have perfect units. We have pounds, weight density. All our areas are counted for, even though our B's we canceled out. But yeah, so from yesterday I have a sine theta, cosine theta, and this is what we're doing the differentiation of. Like last night, this is what we had. We had a cosine theta divided by a sine theta. So is that what we have? See, I'm missing this cosine theta part. Oh, it's because that was my mistake from last night. I think this cosine theta part came in because I was saying, hey, this length, or this has a thick, this has a, I think this goes away, don't quote me. It's because we proved that the force in BC is always going to be less. So once we find the max force in AC, we go buy our steel. And then whatever the weight happens to be, it just happens to be. So that's why this is just a constant over here. So let's rewrite this. So we're going to have, finally, our weight, and we might have made a mistake, but we have P, L, B, C, weight density, the strength and the tensile strength times, oh, but even here, what am I, holy Toledo. Well, we're dividing by the tensile strength anyway. So yeah, so our weight is going to be, yeah, I think we're doing too many steps at once. But that's all right. But we are going to factor out this length, because this length of BC is a constant. That's what they say. It's like, hey, a fixed length right there. So length BC, we're going to divide by the strength. We have this weight density. Now we're going to go 1 divided by sine theta plus 1 divided by sine theta cosine theta. Now, this is cool because we get to do a product rule on this. And I think we can even foreshadow, since I've already done this, it might be good to see if there is, you know, a rule for a derivative of sine theta cosine theta. No, but we're good to go because we're just going to use the product rule. So let's rewrite the product rule as d dx of a product of u and v is equal to u dv dx plus v du dx. See, I even write this right. U dv dx. So u v v u. Perfect. All right. So now we're good to go. Oh, and yeah, this isn't just the derivative of sine. This is cosecant theta plus cosecant theta secant theta. So now in our book, like this, I just won't know. But the derivative of secant, theta, so d secant theta is secant theta tan theta. Derivative of cosecant is negative cosecant theta cotangent theta. Cool. All right. And even from yesterday, yeah, these are downstairs. So we have to yeah, so whatever I did yesterday was probably wrong. So now hopefully we can do it right. Okay. Holy Toledo. Let's get a fresh sheet of paper. And heck yeah. So again, our weight is just a bunch of constants. And then here's the juice. So we have cosecant theta. And see, I've never written cosecant theta. I don't think anyone has. So it almost seems like your brain's going to explode even just when you write it. And the derivative of cosecant gets a little crazy. So now, and then we have secant. Yeah, it's even hard to look at. Okay, so but now we're going to take the derivative of weight with respect to theta. Derivative of the constants just stay outside. We're going to show the chain rule again. So dx uv is equal to u. Why did they choose u and v? They're so easy to get mixed up. But v du dx. All right, heck yeah. Okay, nice. If this goes smoothly, we might be on the home stretch. So, and we're going to say the derivative of cosecant theta, that's the first one, with respect to theta, is equal to negative cosecant theta cotangent theta. I think I can remember that. Derivative of secant theta with respect to theta is secant theta tangent theta. Cool, I can remember that. So now, right here, this is our u, this is our v. Okay, So the first thing is we just take the derivative. So if we're going to take the derivative with respect to theta of this now, we got to do the first term. So we have our constant out here, PLBC, gamma, sigma, and then we have parentheses. Derivative of cosecant is negative cosecant theta cotangent theta. Cool. And now we have our u and v. So at the end, we're just going to have the term u, which is cosecant theta, dv dx, which is this, the derivative of this one, which is secant theta tangent theta, and hopefully this cleans up, and I know a way to clean it up, plus v is secant theta du dx, which is the derivative of a cosecant, so this becomes negative, if I can remember that, cosecant theta cotangent theta. Heck yeah. Tangent is sine theta over cosine theta. Cotangent is cosine theta over sine theta. Yeah, I guess I shouldn't call it inverse tangent. Inverse tangent is not the same thing as arctan or cotan. Or am I even saying that right? Cotangent? Yeah. Cotangent is cosine over sine. Cool. Now, are these cosines to the negative one? Is that what they call arctan? You know, I got to watch that YouTube video. Okay, now we know that this is just inversed. So cosecant, so let's write this again. PLB gamma sigma. So we have negative 1 divided by sine theta multiplied by cosine theta sine theta plus 1 divided by sine theta 1 divided by cosine theta, and then sine theta cosine theta. Sine thetas cancel and we got a cosine squared. Cool. And then minus 1 divided by cosine theta 1 divided by sine theta, and then we have cosine theta sine theta. See, it's the reverse of tangent. Cosines cancel. Cool. So now we have this doesn't cancel. This is 1 over cosine squared theta minus 1 over sine squared theta minus cosine theta over sine squared theta. Cool. And I'm just going to run with it, and then we're going to put this into the calculator. And hopefully this will be the derivative. And hopefully it'll cross the 45. And we'll even type in all this nonsense. So we're going to do 58,000, 24 inches in length, 0.29 for the weight density. We got another parentheses. Divided by 58,000. Cool. And then parentheses 1 divided by cosine x squared, parentheses, minus 1 divided by sine x squared, parentheses, minus cosine x. Alright, more light. Cool. Then we got minus cosine x divided by sine x squared, end parentheses, maybe end parentheses. All right, hopefully that will cross the 45 degree, should cross the 0 at 45, if we got it right. Probably not though, you know what I mean? Heck yeah, look at that. Sweet. That was a humdinger for the calculator so now we're going to go value 45 of this red one. Oh shoot, you know what I mean? Oh, it doesn't cross. Oh man, it doesn't cross at the lowest point. So we're going to trace. Where does it cross? It crosses at 52.5 degrees. So obviously we have some sort of hiccup. I mean, maybe we just came up with something cool, and that's exactly where it should have crossed. But the lowest point, if we trace this out, oh. Let's see, the lowest point. Yeah, the lowest point is right there. So whatever graph that I graphed, I mean, yeah, let's see. Maybe the answer, I've on this problem, I thought I looked in the answer in the back of the book. Yeah. And no, I haven't. No, this is perfect. This is perfect. I've never looked at the answer in the back of the book. We got 50. Well, let's see what we get. So we're gonna do the 0 value of this. We're gonna go left bound, right bound, and then center. I don't know where I got, but yeah. So my answer is 51.8 degrees. So the answer in the back of the book is 54.7. So 54.7 degrees is what they got. And yeah, I haven't looked at the answer in the back of the... I don't know why I was thinking, you know, something magical happened at 45. But yeah, so the answer they got is 1 arc cosine, so 1 divided by cosine theta times, or the square root of 3. 1 divided by the square root of 3 cosine theta. That's what they got. I don't know if my answer actually is more precise since we used, I like the way that I did it. I did the force max in AC, and then I sized AC, and then just by observation I said BC is always going to be stronger. You know what I mean? Plenty strong. So then I graphed it, and then we used the product rule to find the equation for the derivative. It's awful looking. But I think I could even clean this up. I'm just kind of bummed that I'm not getting 100%. So maybe it's because the weight density of 0.29 isn't 100% correct. So let me actually clear this out. And we're going to type it in just like this and see if we get that answer. Alright, heck yeah. And this is a good practice to type in complicated stuff. So I'm going to put a 1 parentheses, and it's got to do the entire thing. So this is the end parentheses for right there. 1 divided by, now I got a parentheses on the opposite of the squared, so cosine x. Yeah, I'm fine with that, squared. So done with squaring that. But now I can just do 1. Yeah, I'm doing as minimal parentheses as possible. 1 divided by sine x, and I'm going to square that. And then minus cosine x divided by sine x, and then I'm going to square that. So I did the minimal amount of parentheses. We're going to graph this, and hopefully, you know, maybe this will actually cross at 54.7. And it was just my understanding of this weight density was wrong for steel. You know what I mean? We were off. So here we go. Zero value, I'm going to go left bound, right bound, and then get it. No, this still says 51.8. So anyway, I'm going to chalk this up as fundamentally, I must be doing it fundamentally different than the answer they got in the back of the book. But I'm fine. This is a two-starred problem, so I'm fine with saying, hey, I found the max force, and I went to the steel yard and sized this accordingly. I'm going to use the same material for both. That's what they say in the directions. And I'm just going to know from my equations that BC is always going to be stronger because I bought that material. Yep. And then figuring out how much with a design load, I'm going to show that I can reduce the weight by choosing an angle of 51.8. So that's the angle I'm going to choose. They chose 54.7. I got to be done with this video because this is the point where it's just like I actually don't know where to go back. You know, sines and cosines are fractions of a whole where just a slight variation, you know, might not be off by much, especially since these are squareds. You know, if one of these isn't squared and this is actually just sine theta, so I can try to account for that, but I don't see that. Cosine squared, sine squared. This is sine squared. Oh, well, no, this is cosine. Oh, yeah, so perfect. So I actually figured out where my error was. I realized that my error was small, and I realized that sines and cosines are fractions of a whole. I'm realizing that we're squaring fractions. I mean, it doesn't make the, you know, if you take 0.5 and then square it, you get 0.25. So that is kind of significant, but okay, so let's right here is probably our error. So this doesn't simplify. So I'm going to go negative cosine theta sine squared theta. This simplifies plus 1 over cosine squared theta. Cool. And then this simplifies to 1 over sine squared theta. Cool. And hopefully my signage is right. So this is a negative, because if you have cosine squared plus sine squared, hey, that's 1, but not cosine squared minus sine squared. There is an identity for that, and that's the one that I want to get more familiar with. When you have sine squared, cosine squared minus sine squared is cosine 2x. It's a double angle kind of relationship. Cool. But let's hopefully say that this is going to be different. And I'll do it on another line, and we'll go negative cosine x divided by sine x squared. Done with that one. Plus 1 divided by cosine x squared minus 1 divided by sine x squared. Alright, graph it. Hopefully it's a different line than this red one. It's going to be black. And hopefully it goes just a little bit to the right. Nah, it's identical. Zero value, left bound, right bound, guess. Yeah, 51.8. Okay, so that wasn't the error, so I still have something fundamentally different. Now, maybe it's not wrong, it's just different than the answer in the back of the book. So that was one way to check the error. I'm going to be done with this video. I think I learned a lot, and yeah. And we got the gist. You know, that's where, like, forget about the differentiation. You know what I mean? Just throw in a few values. You know, I might want to take this to Excel and see what the best ratio is. Like, obviously, it's just where the Again, it's just where the weight is the lowest. But yeah, maybe I will take this to Excel, because just because the weight is lowest doesn't mean that, maybe a few extra pounds to get that extra, a few extra dollars to get a little bit more kilonewtons. You're not getting the best value for the increase in kilonewtons, but at the end of the day, it still might make more sense. Because maybe a 51 degree, or they're saying 54.7. Maybe 54.7, who's going to measure that? That is it's probably doesn't even look good to look at. So why not just say, hey, 60 degrees is your match? So at the end of the day, this 2-star problem, I think I learned, 60 degrees, that's what I learned. You know what I mean? That's why this answer of 54.7, it's a magic trick to look past. Because now you can just know that, I'm going to spend like $1 or $2 more on my material, but I'm going to get more strength. Guarantee. We've already proved that if we do an angle of 60, your design load is going to be greater, but you are going to have to put in a little bit more material. And but it's two things. Yeah, you're actually doing a thinner. Your thickness goes down. So we've played around with this problem so much that, yeah, as your angle goes up, this bar can take more load. You're just increasing the weight because you just have more material. But your initial thickness does go down. And we only have kind of 2 minutes to wrap up if I want to be done with this. But I think if we go back, look at this. This 60 degrees says, hey, if I chose if I chose 1 square inch, like my thickness was about 1. So there you go. So it might make sense just to have a 1 square inch for thickness and width, and choose 60 degrees and call it. Yep. But in this case, if you wanted to carry the 58,000 pounds with 1 square inch, you ain't going to be able to do it. That's why this 0.15. Fundamentally, we do have an angle here. If you want to carry 58,000 pounds with a material that can only take 58,000 pounds, well, you'd have to have it perfectly vertical. So obviously, you have to have a little bit more area. All right, I might spend some more time on this to see what I did with this integration and see how they got 1 square root of 3 arctan or something like that. So anyway, all right, thanks for joining me, and that's a video.